So let's start by looking at this River Valley paper. And I was from River Valley, so my secondary school was River Valley before they turned IP. Then after that I went to RJC. So looking at this River Valley paper sort of like gave me a little bit of memory just by looking at the logo. I can still remember my school songs, and in fact a lot of my friends, they are now teaching in River Valley. So in case some of you here are from River Valley, I probably know some of your teachers. So anyway, we're going to be looking at this River Valley paper. If you have not signed in onto the Achevas TV, the full paper 1 is actually downloadable on the Achevas TV. You just need to sign in, go to online.achevas.com/live. You should be able to get the materials for today, okay? This River Valley paper. And just in case, you can also try to have your MF26, your formula sheet with you. We will probably be referring to some of the formulas here, but and definitely your graphing calculator. Okay, what I hope you can try to do with me, right, is to really have your paper, have your pen, have your calculator with you, and as we go through the questions together, as I try to do the questions here, maybe you can try to follow along and we can try to be doing the paper together from question number 1 to either question number 5 or question number 6. Okay, let's take a look at question number 1 of this River Valley paper. The version that you have should be a full paper that is like this. Okay, I've cut out the different questions, so I'm going to start with question number 1. It is an inequality question. I don't think this question is particularly difficult. It is in fact, I think it is quite an easy question. Oh, by the way, for you guys who are here for the first time, of course it is the first time because this is the first time I am doing my live stream. There is this chat. Okay, it's not exactly a chat, but there is this option for you to ask me questions. So just in case along the way you have some questions, please just post onto that question box that is beside my video right now. And as much as possible, I will definitely read it, okay, but as much as possible, I'm going to try to answer some of your questions, okay? So question number 1. I don't think this is a very difficult question, but in a way, it is a little bit interesting because this question says find the range of values of x that satisfy this inequality here. And the question actually didn't suggest whether you are supposed to use a graphical method or whether you are supposed to use an algebraic method. For those of you here, if you are already preparing to go for your A-levels this year, I am pretty sure you will want to try to use the algebraic method. But please know that using an algebraic method to solve an inequality is not the best possible way. The best possible way is actually to make use of the graphical method. In my weekly class with my students, I've always told them how good graphical method is when it comes to solving inequality that is like this. But of course, with experience, it is actually possible for us to execute something that is like this using an algebraic method pretty well. So I do think if this question were to appear in the exam, I will also want to execute this as an algebraic method, provided, because if some of you are using it if some of you are deciding to continue with this question using an algebraic method, it is okay. It's just that if you can dive deeper into the understanding of algebraic method, there are some conditions that must be satisfied. During the class, I did go through in depth about those conditions, but just for our discussion today, when I look at an inequality that is like this, I want to make sure that 3 things must happen in order for me to decide that I can potentially use an algebraic method. Number 1, I want to make sure that one side of the inequality is going to be made into a 0, and I don't think this is very difficult. And for the other side that is not 0, I want to make sure that it can be factorized into multiples of linear expression. That means even if I manage to factorize them but I don't get a linear expression, I will probably not use an algebraic method. Anyway, let's start. So we have 2x over x plus 5. This is supposed to be less than 1 over x minus 1. So the first thing is I'm going to make sure that one side is equal to 0. So I'm going to bring this over to the left hand side. So this divided by x plus 5 minus away 1 over x minus 1. This is less than 0. One side is equal to 0, and like what I was telling you, I must see the potential of me manipulating this algebra so that on the non-zero side, they must be re-expressed into multiples of linear expression, and I think it is definitely possible for this. Let's try to combine this into one single fraction. So we have a 2x multiplied by x minus 1 minus away x plus 5, this divided by x plus 5 and x minus 1. This is less than 0. So for the numerator, let's expand this and combine together. So we have a 2x squared minus 2x minus x, then minus 5, this divided by x plus 5, x minus 1. This is less than 0. So 2x squared minus 3x minus 5, this divided by x plus 5, x minus 1. This is less than 0. For the numerator, we can factorize. It will be 2x and we will have an x here. Here, I guess I am going to choose this as a minus 5, and here it will be a plus 1. This divided by x plus 5 and a x minus 1. This is less than 0. So now we have one side to be equal to 0, and for the non-zero side, it is multiples of linear expression. If I'm not sure whether I can achieve this, it is actually better for us to just simply adopt the graphical method. Especially for this particular question, we are not even suggested whether we should use graphical or algebraic method. So for here, I'm going to try to sketch a number line to represent what I have so far. So for my number line, I will have a minus 5, a minus 1, 1, and a 5 over 2. We are going to substitute numbers into this entire expression to determine whether it is positive or negative for each of the different values that is between the numbers that I'm seeing here. We can definitely use our graphing calculator and manually sub numbers that is like, for example, something that is bigger than 5 over 2, for example 3, and for example maybe 2. I have actually done the substitution using y1. I'm not sure whether you guys have used it before, but it is actually surprisingly useful if you plan to do substitution. Like for example, this that I have here, right? I basically press this entire left hand side into y1, and after I've pressed this into y1, I will then go back to the main screen. Then on the main screen, I can trigger y1, then bracket 3, because on my calculator, y1, y2, y3, they are just simply representing functions. So if I can press this expression, into y1, then doing a y1 then bracket 3 will actually give me the result when I substitute 3 into this expression. So I get a 1 over 4, so I know it is positive. Likewise, I can then very quickly substitute different numbers, for example 2, into the entire expression, a negative number, so this is negative. Then if you were to continue, it is going to be positive. If I were to continue again, it is going to be negative and positive. We are looking for the set of values of x such that this entire expression is less than 0. So looking at what we have here, the region that is less than 0 is going to be this region and this region. So I have my answer now. My answer is when x is supposed to be strictly bigger than minus 5 and strictly less than minus 1, or x is going to be strictly bigger than 1, strictly less than 5 over 2. Okay, I think this is actually pretty simple, and for most of us, I don't think it is difficult to choose an algebraic method over a graphical method, although I still do think that a graphical method is actually a better strategy for inequalities in general. Next, we are supposed to make use of this to deduce this, and I don't think it is very difficult, right? If you were to look at what that is here, it is pretty obvious that I'm going to be replacing x by modulus of x. So for 2 modulus of x divided by modulus of x plus 5 minus 1 over modulus of x minus 1. This is less than 0. We can see that all the x are going to be replaced by modulus of x, which means that this x over here, I am also going to be replacing it by modulus of x. So, which means that I will have a modulus of x is supposed to be bigger than minus 5 and less than minus 1, or modulus of x is supposed to be bigger than 1, supposed to be between 1 and 5 over 2. If we just make use of a little bit of our mathematical logic, we know that x can never produce anything when it is within the modulus. So modulus of x cannot possibly be between minus 5 and minus 1. So we will never be able to find an x that will satisfy this inequality, which means that for this, we will not be able to get any solution. As for this, what I think we can try do is to sketch a graph. So what I'm going to do is to sketch a graph of y is equal to modulus of x. Okay, actually I saw somebody asking this. Let me just very quickly answer this question first, okay? Somebody was asking whether the stream will be recorded. In fact, we are not sure whether we will want to be recording the stream yet. So I don't dare to promise that this stream will be recorded, but my plan is to hopefully, I can be streaming at least once or hopefully twice a week. Then whether it can be, whether we are planning to go to record this stream, we'll probably announce it again sometime later. We are trying out. Okay, this is Achevas live beta, so we are really trying out something, and to me, I'm pretty excited about what we are trying to launch here on Achevas TV. So anyway, let me continue with this. Okay, for this, I'm going to sketch a graph. So I will sketch a graph of y is equal to modulus of x. And it is an entirely, it is a totally simple graph for us to be sketching. It is a standard graph. Regardless of whether you want to use the graphing calculator or not, I think we can actually sketch it without any help from our calculator at all still. So we can sketch the graph of y is equal to modulus of x. And we are looking at modulus of x to be between 1 to 5 over 2. So I'm going to sketch the line y is equal to 1 and the line y is equal to 5 over 2. So when y is equal to 1, x is going to be either 1 or x can be minus 1. When y is equal to 5 over 2, this here is going to be 5 over 2, or it can also be minus 5 over 2. So we are looking for the set of values of x such that modulus of x, which is the y coordinate of this graph, is between 1 to 5 over 2. So the set of values of x that satisfy this will be from here and here, correct? As long as x is between 1 to 5 over 2, y, which is modulus of x, is going to be between 1 to 5 over 2. So with this that we have here, I can now state the answer. My answer is going to be x to be between minus 5 over 2 and minus 1, or x is going to be between 1 to 5 over 2. Okay. Okay, I do see another question coming in. Let me take a look at this question. Someone was asking whether we can use an algebraic method. Let me show you the question, okay? So someone is asking whether we can use an algebraic method for this last part of question number 1. I assume it is this part that you are saying. So for this part, we can definitely use a more algebraic method. But like what I was saying in the beginning, I do think that as much as possible, we should try to use a graphical method, because graph has the ability to help us to handle a continuous set of values of x, instead of an algebraic method which is aimed to handle more discrete values of x, which means that if I can do this, I can see the set of values almost like immediately. But let's try. Okay, it is possible for us to use an algebraic method. So let's do a quick comparison for a question that is like this, especially when we were not instructed whether we should be using a graphical method or an algebraic method. Let's see what will happen if I were to be using, let's say, a more algebraic method for the last part. So this is definitely still going to be not applicable regardless of graphical method or algebraic method. So let's focus on this. We are trying to look at modulus of x to be between 1 to 5 over 2. which means that modulus of x has to be bigger than 1, this, and modulus of x has to be less than 5 over 2. Hang on, let me remove this question first. Okay, so someone was asking whether we can use an algebraic method for the last part. I totally agree, you can do that, but let's just do a quick comparison how well the algebraic method can be as compared to the graphical method that I've just used. I mean, for me, okay, let us try first, okay, before I give you my opinion. So for this, I know x is going to be less than minus 1, or x is going to be bigger than 1. As for this, I know x is going to be between minus 5 over 2 and 5 over 2. So x is this, and this, what I'm going to do is I'm going to consolidate these two sets of answers here through a number line. So we have a minus 5 over 2, we have a minus 1, we have a 1, and we have a 5 over 2. So for what we are looking at here, x is going to be, if I were to be looking at this set of the solution, x is going to be strictly less than minus 1, or x is going to be strictly bigger than 1. As for this, it's going to be between minus 5 over 2 and 5 over 2. We want this and this, so we are looking for the overlapping region. So it's going to be this and this, which means that x is going to be between minus 5 over 2 and minus 1, which is the same as this, or x is going to be between 1 and 5 over 2, which is the same as this. I mean, we are definitely expecting the same solution, the same answers. But if you were to ask me, there's actually less consideration when I'm trying to use a graphical method to solve for this instead of using a more algebraic method. So to me, if it is possible, I will definitely try to sketch a graph, especially when it is such a simple graph and I can probably come up with the answers faster in the exam and with less consideration, which means that there will be less chance for me to make careless mistakes. So for me, I vote for this. Okay, but of course, different people are a little bit different. You can decide it yourself. Okay. So next, let's take a look at the question number 2. Question number 2 is Maclaurin's question. Let's take a look at it together. Question number 2. Okay, so here. So we have f, if you have y is equal to fx, and we are told that this is going to be passing through 0, 2. This 0, 2 actually gave us a very crucial information. This tells us that f0, this is equal to 2. And dy dx is this. We are supposed to obtain the Maclaurin series of y in ascending powers of x all the way until the x square term. So let me very quickly quote the Maclaurin's formula from MF26 from our formula sheet. So fx here, this is equal to f0 plus x of f prime 0 plus x squared over 2 factorial of f prime prime 0, and all the way. The idea of Maclaurin's is for us to re-express any function into an infinite polynomial. So it goes all the way plus dot dot dot. Let's try to come up with this, the Maclaurin's for y, so for fx. Which means that we need f0, which is fine, because we know f0 is equal to 2. Because the entire idea of Maclaurin's, if we are using this formula, this differentiated formula for our Maclaurin's, our aim is to fill up this, and to fill up this. Because x is the variable, but for it to be customized for this particular fx, we are still lacking in terms of part of the coefficient, which is what we are trying to find. So f0 is going to be equal to 2, f prime 0. I don't think it is that difficult because we can simply let x be equal to 0 into here, and we can find dy dx, and that will be f prime 0. So what we are still lacking so far is f prime prime, which is d squared y dx squared. Let's try to find d squared y dx squared. So let me start with dy dx. This is equal to cosine x divided by 2y. I think I'm going to do a little bit of improvisation. Let me bring this 2y over to the other side. So dy dx. This is equal to cosine x. I'm going to differentiate this with respect to x. So on the left hand side, product rule. So 2y, I'll let it remain. Then we'll have a d square y dx squared. Plus, differentiating 2y, we have a 2 dy dx. Then multiply by dy dx is equal to differentiating cosine x. This gives me a minus sine x. So not exactly the most necessary thing, but I think I am still going to combine this together into one single expression first before I start my substitution. So now we have f0, we have the expression for dy dx, we have an equation for d square y dx squared. Let's start to fill in part of the coefficient so that I can generate the Maclaurins in ascending powers of x for y. So I am going to let x be equal to 0. When x is equal to 0, y is equal to 2. This is given to us by question, and this gives us our f0. So this done. And we want to try to find dy dx. dy dx is going to be equal to cosine x is equal to 0 over 2y. And y is 2 when x is equal to 0. So it's going to be 2 times of 2. This is equal to 1/4. And this is equal to f prime 0. So we have this, check. Then finally we are looking for d square y dx square. So d square y dx square, this is going to be equal to minus sine x, which is 0. So minus sine 0, then minus 2 times of dy dx. When x is equal to 0 is 1/4. So I have a 1/4 square divided by 2y. So 2y, y is going to be equal to 2 when x is equal to 0. So 2 times 2, this gives me a minus 1 over 32. So this, check. Now with all this, we can quote y. We will be able to quote y, which is my fx, and y is going to be equal to f0, so it is 2 plus x times of f prime 0, which is 1/4, plus x squared over 2 factorial of f prime prime 0, and that is minus 1 over 32 plus dot dot dot. So this is equal to y. Y is going to be equal to 2 plus 1/4 x minus 1 over 64 x squared plus dot dot dot. So we have our answer for part 1, and let me write it down here. We will probably be making use of it later on. So y is equal to 2 plus 1/4 x minus 1 over 64 x squared, and all the way until infinity, Maclaurins. The aim is for us to be generating an infinite polynomial. And for part 1, there's still a little bit more. We are supposed to write down the equation of the tangent to the curve when y is equal of the curve y is equal to fx when x is equal to 0. So we will just go for what we know about. We can just go for the structure that we know about tangent, generating a tangent for a curve. That means when x is equal to 0, in order for me to generate a tangent, we just need the x coordinate, which is already 0, the y coordinate. When x is equal to 0, the y coordinate is 2, and the gradient. So next, dy dx. When x is equal to 0, the gradient is equal to 1/4. So that we have to, so we have all the conditions that are necessary for us to generate the tangent, and the tangent will be y minus away the y coordinate is equal to the gradient, multiplied by x minus the x coordinate, which is 0. So y is equal to 1/4 x plus 2. That is for this. Next, part 2. Let me erase this first. So for part 2, we are supposed to show that y is equal to this. And which means if the piece of information that I have so far is not exactly fx. I mean, if I'm given fx, I will not be asked for y, right? So the only sensible piece of information that I'm going to make use of for part 2 is probably this. dy dx is equal to cosine x over 2y. Because if I'm doing part 2 of this River Valley Prelim paper 1 from 2019. So what we are supposed to do, since this is probably the best information that we have so far, of course we can make use of this, but I do think that this is a little bit easier because what we can try to do is to work backwards. We can work backwards, then we can probably find an equation or an expression, for between x and y, and hopefully that equation is going to be looking like this. So from here, if we want to work backwards, is there a topic or is there a concept that has helped us before to remove the dx so that I can get all the y and x? Yes, there is. So we have to revisit this other topic called differential equation. In differential equation, comparing it to this first order differential equation that we have here, this is a variable separable format. If you were to take a look at the theory outline on the Achevas TV, where there are 2 ways for us to solve differential equation, because in our syllabus there are also just 2 kinds of differential equation that we are supposed to solve. Anything that is not these 2 kinds are most likely going to be manipulations and improvisation. So the first kind is the simple differential equation where dy dx is expressed in terms of just simply x. Another kind is when dy dx is expressed as both x and y. So what I'm going to do is to treat this as the second kind, and it has to be the variable separable kind. It is the variable separable kind, and I am going to bring the 2y over to the left hand side. So I have this is equal to cosine of x. So what I'm going to do is I'm going to integrate both left and right hand side with respect to x. So integrating the left hand side with respect to x, I will be left with this dy. Integrating the right hand side with respect to x, I will have this cosine x dx. So for this, it is 2y squared over 2 is equal to this. This is going to be sine x. And let's not forget an arbitrary constant plus c. So we have a y squared is equal to sine x plus c. We are supposed to show this. We are probably on the right track because there's at least a sine x here. And if we were to make y the subject, we will square root this, so there is also a square root here. Let's try to solve for c. We have a piece of information that will allow us to solve for c, and that is when x is equal to 0, y is equal to 2. So let me go for that. When x is equal to 0, I know y is equal to 2, which means that 2 squared, this is going to be equal to sine 0 plus c. Sine 0 is 0. This tells me that c is 4. Super nice, because we have a 4 here also, and then there's a sine x here, which means that y squared, therefore y squared is now going to be c, which is 4, plus sine x. But y is still going to be plus or minus square root of 4 plus sine x. But what we are supposed to show is positive square root. So we need to verify whether for the information that is given, whether it is supposed to be plus or whether it is supposed to be minus. And to do that, I'm going to make use of this piece of information one more time, because I know when x is equal to 0, y is going to be positive 2. So when x is equal to 0, y, it should be positive square root of 4 plus sine 0 to give me a positive 2. Because if it is otherwise, if it is the negative, it is very obvious that I'm going to be getting a minus 2. So this is not going to be my answer. Therefore, I know y is going to be positive square root of 4 plus sine x, which is what we are supposed to show here. When I was looking at this question, I was just wondering, okay, I mean, I don't think the next thing that I'm going to say is a better solution to this. In fact, I think this is probably the best if you were to I mean, if I were to choose, I would definitely try to go for this instead of what I'm going to say next. But I'm just curious because I feel that it is actually maybe still possible, maybe still acceptable if I were to do a bit of verification to show instead of doing all the differential equation to show. Okay, a little bit more risky, so I don't encourage you to do this, but just for a little bit of proof of concept, what if you were to try to verify that this really satisfy the information that is given so far? Which means that if I were to take y to be equal to square root of 4 plus sine x. First, if this is really the y at equal to fx, is really this here, that means it must satisfy this, right? So I'm going to try to do a check whether it satisfies this condition. So I can try to let x be equal to 0. And when I let x be equal to 0, y is going to be equal to square root of 4 plus sine 0. And this will give me a square root of 4, positive square root of 4. This is equal to 2. So therefore, it passes through the point 0, 2. Number 1, verified. And I want to do another verification. You know why this one single verification is not enough? Because what if there's going to be a plus c? Which, okay, in this case, there's no plus c, okay? But we probably should try to do another verification, since this is another piece of information that is given to us also. So what if we were to try to find dy dx for this version? So from here, if I were to square both sides, we have this, then 4 plus sine x. Differentiating this, it is 2y of dy dx. This is going to be equal to cosine x. Okay, true enough. It satisfies both of the information that is given to me by the question. So in a way, I have verified that y is equal to this is going to be fx. But anyway, let's go for my set of solution here. Let's move on to part 3 of the question. So for part 3, we are supposed to use the result in part 2, and assuming that x is sufficiently small, we are supposed to once again try to obtain the binomial series for y. So I'm going to be making use of y is equal to square root of 4 plus sine x. The first thing that we should try to do is to re-express sine. Why do we have the motivation to re-express sine? Because according to what the question says, we are supposed to be expressing it in terms of polynomial, because we are looking at anything that is x to the power of 3 is supposed to be negligible, and we are supposed to be looking at a binomial series for y. Okay, both direct me to tell me that we are looking for polynomial, which means that sine, I will also want to try to convert it into a polynomial. And I'm going to make use of my formula sheet, my MF26 again. So let me quote it down here. On my MF26, I have a sine x. When I re-express sine x as a Maclaurin, as an infinite polynomial, according to my formula sheet, this is x minus x to the power of 3 divided by 3 factorial plus x to the power of 5 divided by 5 factorial, and all the way until infinity, an infinite polynomial. So I'm going to start by re-expressing this sign here. So it will be square root of 4 plus sine x. And since the question says x to the power of 3 is supposed to be negligible, so all this will be negligible, which means that sine x is going to be approximately just x. And I'm going to re-express this again. I'm going to re-express this as 4 plus x to the power of half. And then I'm going to make use of Maclaurin's. So I want to refer back to my MF26 again. In my MF26, I have a Maclaurin's version for binomial expansion. So 1 plus x to the power of n, this is, according to my formula sheet, this is 1 plus nx plus n of n minus 1 divided by 2 of x squared and all the way until infinity. So now from here, in order for me to make use of this as a formula for me to execute my binomial series, what I'm going to make sure of is to make sure that 4 here is algebraically 1, which is I mean 4 should become, if I'm going to be making use of this formula, I need to make sure that whatever that is at this position, it should be 1. And 4 is definitely not 1. I'm going to factorize out 4. We will just need to do a quick algebraic manipulation since we are using a result that is like this. So factorizing out 4, it will give me a 4 to the power of half. This will be 1 plus this, it will be x over 4 to the power of half. So what we are going to be doing is to replace all the x by x over 4. 4 to the power of half here is 2. Then it will be, now we can make use of what we have in our MF26. It will be 1 plus n. n is half. So here I will have half. And x is going to be replaced by x over 4. Then plus here is half. Half minus 1 is minus half. Then this divided by 2. X is going to be replaced by x over 4 square. And the next term is going to be x to the power of 3. And the question says it is negligible. So I'm going to just leave it in the dot dot. So this is going to be equal to 2 multiplied by what I have here is going to be a 1. If I were to just expand it in, okay, I mean, let's just expand it. So if I were to expand in, it will be 2. Expanding this in, it will be 1/4 x. And multiplying this in, we will have a minus 1 over 64 and x to the power of 2. Plus dot dot dot. Question number 2. Part 1, part 2, part 3. Okay, done. Let's move on to question number 3. River Valley 2019 Prelim, Paper 1, question number 3. We have this. This is a rational expression, and we are looking at a curve. Y is equal to this, which represents the graph, the expression of a rational function. So we are supposed to show that A is equal to 9 and B is equal to 18. We are given 2 pieces of information. We are told that the curve passes through this and it has an asymptote of x is equal to 3. So for the very first part, the curve passes through this. So at the point 9 over 2 and 0. At the point 9 over 2 and 0, I know x is equal to 9 over 2, y is equal to 0. So substituting that in, we have a 0 is equal to 2 times of 9 over 2 minus a, divided by 2 times of 9 over 2 squared minus b. And for the denominator, I'm going to just simply multiply across. So I have a 0 is equal to 9 minus a. This tells me that a is equal to 9. Okay, I have shown the first part. I see a question that is here that is asking me about the previous question. Hang on, let me think whether I want to revisit that question. Somebody actually asked me this. Why did the question phrase it in such a way that they ask for a binomial expansion instead of the Maclaurin series? It is confusing. To me, binomial expansion is actually part of Maclaurin series. So I personally don't really find it that confusing. I guess one of the motivation that the question is asking you for the binomial series is probably because because they are actually very similar. I mean, binomial series is a subset of Maclaurins, right? If you were to look at your formula sheet under Maclaurins, is where we find our binomial series. But what if the question were to ask you, let me ask you who have asked this question, okay, what if the question asks you, can you obtain the Maclaurin's series for y? I do think, because that is probably not the intention of the whoever setting this question, I do think it will actually cause some students to do all the differentiation to this to find the expansion. And I don't think the teacher or whoever said this question is that mean, because since we have something that is this, and if we can just approximate sine x to x, and this will just simply follow a standard result that is already in our MF26, that is already in our formula sheet. So why not just use the formula that we already have instead of having to do everything through differentiation from scratch. In part 1, that Maclaurin series through differentiation has already been tested. So I do think that one reason why the setter specifically chose the word binomial series instead of Maclaurin's is to actually direct students to make use of the result from the MF26 instead of making some students misunderstand and then try to do all the differentiation for this over again. But of course, if they were to say binomial series and you went to do the differentiation version, you will actually be marked wrong for this because the question specifically mentioned that you are supposed to use the Maclaurin's series version. You're supposed to use the binomial series version, okay? Anyway, let's continue with this question here, okay? So question number 3. We have already solved for A. And I'm really hoping, okay, that you guys are doing this together with me right now. And we want to solve for B. To solve for B, I'm going to make use of this piece of information here. X is equal to 3. X is equal to 3 is the vertical asymptote. And if you were to look at my theory outline on the Achevas TV, vertical asymptote is defined as a value of x that causes y to be undefined, which means that if I want to be really specific in the way that I present my solution here, it is when x is equal to 3, y is supposed to be undefined. And for y, taking up an expression that is like this, to be undefined, that is when the denominator should be equal to 0. So when x is equal to 3, y is undefined, that will be when the denominator is equal to 0. Which means that when I substitute 3 into the denominator, it should give me a 0. So b here is equal to 18. So shown, done. So this one done, this one done. Which means that now I will be working on, at least for this, we will be working on 2x minus a, which is 9, divided by 2x squared minus b, which is equal to 18. So I'm working on this graph, and part 2 we are supposed to sketch this graph. I was a little bit surprised because I thought it is quite a simple graph, and yet River Valley gave 4 marks to sketch a graph. And I've always been telling my class, during my tuition class, I've always been telling them, if you want to master curve sketching, please learn that your calculator is not going to be 100% dependable. The best way to view our graphing calculator is to view it as a companion, but it is going to give you only 50% of the answers. And unless you have equipped yourself with another 50%, or else there is always that risk that you're not going to get full marks for a graph sketching question. Let me show you why this graph is actually more difficult than what it may seem. Okay, maybe this is not a very difficult graph, right? Just press it into the calculator. I have actually pressed it into the calculator. Let me show you what I have from my calculator. I get this. Okay, this is what I've gotten in my calculator. And when we are trying to sketch graph, I do think it is always going to be a very, very good habit. We will not sketch what that we see immediately on a calculator first. It is a better habit if we can just sketch in the asymptotes first. Because the asymptotes divide my graph, so it makes the process of me churning out the graph a bit more organized and a little bit neater. I'm not talking about making the graph beautiful or pretty, I'm talking about generating a set of solutions that is neat and presenting all the necessary theoretical aspect of the graph. So I have the motivation to sketch in all the asymptotes first. So I'm going to do that. My graphing calculator will not show me those asymptotes, but I'm going to make sure that with my own analysis, I'm going to try to sketch out all the asymptotes myself first. So we have an x-axis, we have a y-axis. This graph obviously has a vertical asymptote of x is equal to 3. But if I were to look at the denominator, that is where I'm going to be getting all my vertical asymptote. And if I were to let the denominator be equal to 0, I'm going to get x squared to be equal to 9. So x is going to be equal to plus or minus 3. So on top of 3, we have another vertical asymptote, which is at minus 3. Let me sketch it down here. So this vertical asymptote is probably what that is missing here on my graphing calculator. Then I have another 3. So x is equal to minus 3 and x is equal to 3. This has a horizontal asymptote also. What is the definition of horizontal asymptote on my theory outline? I define horizontal asymptote as the behavior of y when x tends to plus or minus infinity. So when x tends to plus or minus infinity, y becomes 0, right? X squared. So when x tends to plus or minus infinity, y becomes 0. So y is equal to 0 is the horizontal asymptote. Let me now start to sketch in the graph. So for this part of the graph, okay, it is going to be here. And let's make sure that we sketch the graph tending towards the asymptotes. So towards asymptote. As for this part of the graph, it is going to be something that is like this. If I were to press it into my calculator, I'll see my minimum point as somewhere that is in the first quadrant. So it's somewhere here. This will have a coordinate, let me read out to you, it is a coordinate of 1.15 and a 0.436. As for this is where I think some of us may make a mistake, because I do think it seems more like the fact that this part of the graph is going to look something that is like this. From here, I do think that quite a lot of people will draw it this way. But if you were to scrutinize the graph, this screenshot that I'm giving you here, this screenshot is a zoom standard. Under your graphing calculator, I chose a zoom standard, which means that I'm going to be going from minus 10 for the y, and 10 for the y, and minus 10 for the x, and 10 for the x also. So I'm doing this, but can you see this part here? I mean, we need to start to get a bit more sensitive to the graph, especially for most of us, we are going to be doing our A-levels this year. So when I see a graph that is like this, can you please take note with me, together with me, right, that this part of the graph seems to be a part that is a little bit above the x-axis, right? I mean, it does seem like it is a little bit above the x-axis, unlike this, right? Unlike this. This is obviously entirely below the x-axis. This seems to be suggesting that it is a little bit above the x-axis, but this question is actually very, very well set, because from the very beginning, the question has actually already hinted to us that, hey, there is an intersection with the x-axis, and that intersection happens at 9/2, 0. 9/2 is 4.5, which means that the intersection 1, 2, 3, 4, 4.5, there is supposed to be an intersection here. The graph starts from below, there's an intersection here, which means that the graph must go above the x-axis, right? So if you were to scrutinize this graph a little bit more, and you use this as your hint, this graph should start from here, because that is what I see on my graphing calculator. This graph should start from here. It should pass the x-axis, and this place where it passes the x-axis is at 9/2 and 0, this point. And it will reach some kind of maximum point, and you will turn back down again to the x-axis. Of course, you can try to zoom into this area to analyze, or you can look at this expression here, and if x tends to positive infinity, you know that this will tend to 0. That is why I know the y coordinate will go back to 0. So here you make a maximum point turning back to 0. And this, if you were to press into the calculator, it has a very, very small y coordinate. So I want to make sure that this point is below this point. It has a y coordinate of 0.436. This point over here has an x coordinate of 7.85. The y coordinate is way less than this. It's a super micro tiny little value here, 0.0637. We have super tiny y coordinate here. So we have this. This is my graph of y is equal to this. Oh, there's actually one more point that I probably should try to write down. It is this point. That is when x is equal to 0. So when x is equal to 0, this point here is half. So I have this. So this is my graph of y is equal to 2x minus 9 over 2x squared minus 18. Okay, I have this graph, and the question says hence. Let me erase this. The question says hence, giving a reason, deduce the range of values of h such that this graph and this curve C has exactly 6 distinct points. So, intersect C at exactly 6 distinct points. First of all, I really need to make sure that I understand what the geometry of this graph. If you have looked at your conics, this is actually an ellipse, right? So this that we are looking at here is an ellipse with the center at 8, 0, 8, 0. And for this ellipse over here, it has a vertical radius of 10, because this is 100. So this is like 10 square, a vertical radius of 10, and it has a horizontal radius of h. So we have this ellipse here. If I were to try to see it here, if I were to try to see this ellipse here, the x-coordinate of this maximum possible point is 7.85. So that means the center of this ellipse must be on the right hand side of this. So it should be somewhere here. So we are looking at 8 and 0 here. So now let's try to see, okay, if I were to sketch an ellipse where the vertical radius is 10, wow, goodness, this is just 0.436. So 10 will probably be way up somewhere here. Okay, so 10 will probably be here, and which means that if I were to go down, it will probably be something that is like minus 10. So if I were to continue with this ellipse here, it will definitely make an intersection here. So one intersection, we want 6 intersection. So it will make one intersection somewhere all the way, okay, like pretty far away. So it will make an intersection here with the curve. If I were to extend the curve, so the ellipse will probably come down one intersection, and it is so far high up, so it should cut. Okay, actually this depends. Okay, it's here. So it depends on the horizontal radius. If the horizontal radius goes beyond this point, then at least it's going to cut at the second point. One point here, second point here. Then if the horizontal radius goes to all the way to here, that means if I were to be drawing the ellipse all the way until here, okay, which means that I'm assuming the h is 8, then it will cut 1 point, 2 points, 3 points, coming back down 4 points. And the question says that we need to have 6 intersections. So we already have 4 if I were to let the radius be this 8. What if I were to let the radius be all the way until here? Like this. So here it will be coming down. So I will have 1 intersection, 2 intersections, 3 intersection. Here, when it comes down, you have the 4th intersection still. We are still going to be having 4, which means that with our analysis so far, we know h, which is going to be the horizontal radius, must exceed this length. Here is 3, and here is from 0 to here is 8. So I know h must be strictly bigger than 3 plus 8, which means that I know at this point h must be strictly bigger than 11. But the idea is, but the challenge is how much bigger than 11. And I'm looking for h as a positive integer, as it's an integer value, and we are looking for the range of values of h. So if it is, it cannot be equal to 11, because if it is equal to 11, it is never going to give us the 6th intersection. So it must be strictly bigger than 11. So how about 12? 12 is, I do feel that it is very difficult to analyze based on pure observation. I was looking at Real Valley's solution. I didn't really see how they analyze when h is more than 11. So I personally think a slightly better way than to just simply say observation, because in their solution they just simply state observation, is to do a verification. But of course, if you're to do a verification, I do think that they should have given more marks. So I do think that there's a little bit of flaw in their solution right here and the marks allocation. So what I'm going to try to do, if I were to try as much as possible, okay, because I know observation is not going to give me an accurate solution, what I'm going to try to do is I'm going to try to sketch this. And since h is going to be, since we already know h is going to be bigger than 11, I'm going to try 12. Then if 12 doesn't work, I'm going to try 13. I'm going to try 14. So we are doing it a little bit more quantitative manner, and I don't think it is very difficult. Let me show you why I don't think it is very difficult. So if I were to take this x minus 8 squared, this divided by h squared plus y square over 100. This is equal to 1. I'm going to make y the subject because what I'm planning to do is to sketch the graph of this ellipse together with this. So y square over 100, this is equal to 1 minus x minus 8 square, this divided by h square, which I am subsequently going to be letting this be 12, 13, 14, and so on. So y here is going to be equal to plus or minus 10 of square root of 1 minus x minus 8 square over h square. Plus minus 10, if I were to go for plus, it is going to be this top half of the ellipse. If I were to go for minus, I'm going to be going for the bottom half of the ellipse. According to what we are analyzing here, my problem is the bottom half, whether the bottom half will be able to cut this portion of the graph at 2 points, because for the rest of the parts, we are definitely achieving 4 intersections already. Okay, so it is whether the horizontal radius should go, it should go beyond this point, the horizontal radius, but how much it should go beyond this point. When I let h be equal to 12, let me show you what I've gotten on my graphing calculator. Okay, and this is what I've gotten on my calculator when I let h be equal to 12. Okay, when I let h be equal to 12, I got this, and now I see it. When I let h be equal to 12, I have one intersection, I have another intersection. And h is an integer value. H is an integer value that is bigger than 11. Therefore, from my observation, with the second graph that is drawn based on the fact that h is equal to 12, I know h has to be bigger or equal to 12. Okay, and this is my final answer. Let's move on. Let's look at question number 4. Question number 4 is a functions question. In fact, when I was doing this paper, one thing that I realized is that the first few questions are actually pretty okay. It's not exactly the easiest. For example, I do think that part 3 is not going to be that easy in the exam because of this extra observation that we are trying to talk about. But what that is going to be more difficult are actually the next 50%, the later 50% of this paper. We'll probably not get a chance to do that today, so very likely we will be doing the next 50% during our second session. So anyway, let's take a look at question number 4. It is the function question. Okay, we are given now an inverse function, and the question says that an inverse function is when f is equal to f inverse for all x in the domain of f. So part 1, if we are given this, we want to show that f is a self-inverse. So we are trying to show that f is self-inverse. So the first thing that I'm going to try and do is to show that f is equal to f inverse in terms of its expression. So I am going to let y be equal to fx, which means that y is equal to ax plus b divided by cx minus a, where x is supposed to be all real numbers and x cannot be equal to a over c. And I can understand why x cannot be equal to a over c, because that is the value of x that caused the denominator to be undefined. We are going to try to make x a subject in order for us to find the expression for f inverse. So let's cross multiply this. So we have a cxy minus ay. This is equal to ax plus b. So cxy minus ax, this is equal to ay plus b. So if I were to factorize out x, I will have a cy minus a. This is equal to ay plus b. So x is equal to ay plus b divided by cy minus a. So from here we can deduce the expression for f inverse, and that is ax plus b over cx minus a. And this is the same expression as fx. we have only shown one part, which is the expressions are the same, but it doesn't mean yet that it is true for all domains of f. So in order for me to show this, I want to show that their domains are also synchronizing to each other. So in order for me to find the domain of f inverse, it is equal to the range of f. And for us to find the range of f, let's sketch the graph of f. So I'm going to sketch the graph of y is equal to fx. The y-axis, I have it here. The x-axis here, x and y. This has a vertical asymptote. It has a horizontal asymptote. For the expression that is here, the horizontal asymptote is going to be the coefficient of x divided by the coefficient of x in the denominator. So the horizontal asymptote is y is equal to a over c. Vertical asymptote is x is equal to also a over c. Or of course, you can do a long division. And even after you have done a long division, it should adopt a form of a over c plus the remainder out of your long division divided by cx minus a. Okay, but since the highest power, the degree of the polynomial in the numerator and the degree are the same, so no matter how many times you do your long division, the horizontal asymptote will just simply be the coefficient of x, the coefficient of the highest power divided by the coefficient of the highest power in the denominator. So a over c, we are supposed to sketch the asymptotes first. Then we fill in the rest of the graph. The question tells me that a, b, c, they are positive, which means that a over c is a positive number. I will have this. So this is a horizontal asymptote, y is equal to a over c. A over c is a positive number. So x is equal to a over c will be something that is like this. If I were to try to sketch it based on some positive numbers that I put into my graphing calculator, I will get a shape that I can replicate it here. I will get something that is like this and this. Okay, this is the graph of y is equal to fx, and y is equal to fx tells me that the y coordinate that are here represents the output of the function f, which means that from this graph, just by reading all the y coordinates, consolidating them should give me the range of f. So the range of f, looking at what I have here, is from minus infinity to a over c, or from a over c all the way until infinity. Okay, but not including a over c, since this is horizontal asymptote and the graph actually never cut the horizontal asymptote. So this is going to give me the domain of f inverse. And what is this set of value? It is exactly the same as this. That means what we are getting here is exactly the same as the domain of f. So now the expressions are the same, the domains are the same. Therefore, I can say that f is self-inverse. Okay, next, part 2. So for part 2, we are going to try to make use of part 1 to deduce f2. So for f2x, this is the same as ffx. But this is just notation. f2 is ffx, f3 is fffx. So f2 ffx, and I know that f is the same as f inverse. That's what I've proven for part 1. This function that is given to me is a self-inverse function. So I can also view this as f of f inverse. So this is equal to x. And we are supposed to try to state the range of f2. To state the range of f2, one very quick way, although the solution may be a little bit more tedious, but I think our processing wise is actually pretty straightforward. I can just simply see this as a composite function. A composite function ffx, which means that the domain of f2 is going to be the same as the domain of the first function, which is the domain of f. So this is going to be from minus infinity to a over c, or from a over c all the way until infinity. It is this. And the expression of this composite function is x. So if I were to just do a quick sketch, isn't this like super easy to sketch? This is just in accordance to the line y is equal to x, except that I need to consider this as the domain. So y, x. So it will be that 45-degree line all the way until a over c. It is a hollow dot all the way. This is the graph of y is equal to f2x. And this value here is a over c. And since this synchronized to the line y is equal to x, so if the x is a over c, the output will also be a over c here. So a over c. But if I were to consider it based on the from the perspective of f2x, that means from what I see here, I can now simply quote the range of f2 by reading and consolidating all the y coordinates that are on this graph. It is going to be from minus infinity all the way until a over c, or from a over c all the way until infinity. Okay. Next part 3, I find is a strange question. It's strange because I cannot really understand the intention of this question. Maybe there is a obvious intention, but okay, it's not obvious. At least it's not obvious to me. But there is probably some intention that I couldn't see yet. So for part 3, we are supposed to solve this equation. F inverse x is equal to x. One thing that we should try to take note of is that on the left hand side here, we are looking at a function. And for this f inverse x function, we know that f inverse has a domain, right? Just now we have already checked it out. The domain of f inverse is from minus infinity all the way until a over c, or from a over c all the way until infinity, which means that x cannot be equal to a over c. X is all real numbers but cannot be equal to a over c. So whatever answers that I've gotten here, let's make sure that we don't accidentally include a over c. Okay, so f inverse x, we have already found the expression. In fact, it is exactly the same as the expression for fx. So this is going to be ax plus b over cx minus a, and this is equal to x. We're just trying to make x the subject. So from here, I'm going to cross multiply, and we will have if I were to cross multiply, we will have ax plus b. This is cx squared minus ax. I'm going to move everything over to the right hand side, so cx squared minus ax, minus ax, so minus 2ax. So minus 2ax minus b. This is equal to 0. I am going to try solve for x, and I guess we can make use of the quadratic formula. So it will be minus b plus or minus square root of b squared minus 4ac. The quadratic formula, and this is going to be divided by 2c. So we have a 2a plus minus square root of, this is 4a squared plus 4bc. This divided by 2c. I guess we can factorize out 4, and square root of 4 is 2. So this is equal to 2a plus or minus 2 square root of a squared plus bc. And this is going to be divided by 2c. So I've gotten two answers, and they are 2a over 2c, that is a over c, then plus or minus 1 over c of square root of a squared plus bc. Okay, I'm going to accept both answers because I know that I can accept answers as long as they are not a over c, and this is not a over c. Okay, so this is part 3, which is the one that I don't really see the intention, a more H2 math value kind of intention for this question. But anyway, it is good marks to get, 3 marks, not bad. let's continue. Let's look at part 4 of this question. I'm wondering whether there's a chance for us to do question number 6, but anyway, we will definitely be able to do question number 5 together. And a is equal to 2, b is equal to 5, c is equal to 3, which means that I'm looking at an fx now. Okay, let me use red color. I am looking at an fx now. That is when a is equal to 2. So we have a 2x plus bb is 5 divided by c is 3. So 3x minus a is 2. And x will be all real numbers, and x cannot be equal to a over c, okay, which is going to cause the denominator to be equal to 0. So part 4, we want to show that a composite function fg exists. So to show that the composite function fg exists, if you were to check out the theory outline on Achevas TV, we can actually have a pretty useful schematic to represent composite function. It can be something that is like this, where x is going to pass through first g, then it's going to pass through next f, and what is going to come out from f is going to be the output from the composite function. In order for fg to exist, I know this part must be able to be connected together. So in order for here to be connected together, I just need to make sure that whatever that comes out from g, which is the range of g, it must be entirely accepted by f, and that will mean that it should be a subset of the domain of f. So we want to make sure that this happens, and I want to discuss that in my solution. We already have the domain of f, all real numbers except 2 over 3. What we don't have is the range of g, and to find the range of g, let's sketch the graph. Like what I always tell the students in my weekly class tuition, for the range of a function, we should sketch the graph. We must sketch a graph. As long as the domain that we are looking at is a continuous set of numbers, we should always try to aim to sketch a graph. So this is going to be equal to gx. And this is a simple graph to sketch. We can either use our graphing calculator, and I guess for some of you at this stage, you probably can already be sketching this graph as a standard graph with some memory from your secondary school and experience from from your JC. This graph is going to be something that is like this. The graph of y is equal to e to the power of x plus 2. It is e to the power of x translated by 2 units in the positive y direction. And here is when x is equal to 0, that will be at 3. So 0, 3. So looking at this, we can see what is the range. The range of g that we are looking at here is from 2 all the way until infinity. And the domain of f is from minus infinity all the way until 2 over 3, or from 2 over 3 all the way until infinity. So I can see that 2 to infinity will go into a region that is like this entirely. So it is a subset. Therefore, we can say that the composite function fg exists. Next, by considering the graph of f, or otherwise find the exact range of fg, we should consider the graph of f. It is actually easier if I were to do that. So let me try that as my solution. I'm going to consider the graph of f. So if I were to look at part, let me look at part 5, and then let me write it down here. By considering the graph of f, which we have drawn it a few times already, isn't it? So the graph looks something that is like this, except that now we have numbers to fill in. So I have this graph. Okay, it has a horizontal asymptote, like what we have done just now. So my horizontal asymptote is 2 over 3. So we have a y is equal to 2 over 3. We have a vertical asymptote of 2 over 3 also. That is the value of x that causes y to be undefined. So this x is equal to 2 over 3. And if I were to sketch it on my GC, it is going to be something that is like this. And the other part of the graph, it should tend, let me draw it properly. So it should tend towards the asymptotes. So my graph should be this, and going all the way down, tending towards the asymptote. This point and this point here, when x is equal to 0, when x is equal to 0, y is minus 5 over 2. And when I let y be equal to 0, x is also minus 5 over 2. So I have minus 5 over 2, 0 here. This is my graph of y is equal to fx. By considering the graph of f, I want to find the exact range of fg. So what we are going to try to do is to look at the last function in our composite function, that means f. So we are looking at this. Okay, we are looking at f. And for the function f, we do know what is the domain, right? The domain of f is from minus infinity to 2 over 3 or from 2 over 3 all the way until infinity. But what that is happening in our composite function is that it is not this set of value that go into f. The set of value that go into f is what that comes out from g. And what that comes out from g is from 2 all the way until infinity. So from 2 to infinity is going to go into f. So this becomes the new domain. Let's say 2 is here. So from 2 all the way until infinity, not equal to 2, so strictly bigger than 2, which means that I'll be looking at here all the way until infinity. From 2 all the way until infinity goes into f, and whatever that comes out with this new set of value will represent the range of the composite function fg. Okay, so for what we have here so far, I'm going to let this go into the I'm going to let 2 goes into this. So when I substitute 2 in, it is going to be, let's say f2 is going to be 2 times of 2 plus 5. I'm trying to find the corresponding y value for x is equal to 2. So I have this divided by 3 times of 2 minus 2, and this is going to be equal to 9 over 4. So I can see that this y value here is 9 over 4. So this is the set of values of y that is coming out from, this is the set of values that is coming out from the function when 2 to infinity goes into the function f. So from here we can deduce the range of the composite function fg, and that is going to be from this number 2 over 3 but not equal to 2 over 3. So it's going to be from 2 over 3 all the way until 9 over 4, not inclusive of 9 over 4. Okay, this is my last part. Let's do one more question. Okay, I think we will probably overshoot 9:30 a little bit, probably another 15 minutes. We should be able to get the last question done. The last question, it looks very intimidating. I can imagine if I were to be the River Valley, if I were to be a River Valley question, if I were to be a River Valley student, whom I was many years ago, if I were to be doing this question last year, I will probably I'll probably be so intimidated when I see something that is like this. In fact, when I was in JC, we do learn this kind of hyperbolic function. If I can remember correctly, this is called cosh. This is, I think it's called sine or shin. This is tan. This is sec. Then this is cosec. So we are given this hyperbolic function. Anyway, it doesn't really matter. It is not in our new H2 math syllabus anymore. It was in mine the last time. So we are given this. Okay, it doesn't matter. We will just react according to what we see. If it is a knowledge that we don't already possess, the question should have the responsibility to give us whatever that is necessary. So let's not worry. Let's see what that is given to us by the question. We want to part 1, express tan x in the form of this. And we are already given the definition of tan x. It is very similar to tangent. So we just need to follow the instruction that is given to us by the question. So part 1. Part 1 over here is tan x. Where tan x is given to us as shin or sine x over cosh x. And this is equal to sine x. This is going to be this. So we have a e to the power of x minus e to the power of minus x. Let's do this question together. Okay, in case you are actually watching me doing this, I do think that this is going to be a very good practice, because once you write it down, you will realize it's not as difficult. If you were to try to follow me for this question, okay, you can probably still follow, but you won't feel how tangible it is, when you're doing a question that looks seemingly intimidating, but most of the instructions are actually given to you in details, and I don't think we need to worry about this kind of question in exam. In fact, we should embrace this kind of question. So cosh is this. So it is going to be e to the power of x plus e to the power of minus x divided by 2. So the 2 and 2 can be cancelled. We have a e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. We are supposed to express it in terms of e to the power of minus 2x. So to do that, let's do an algebraic manipulation. With the consideration of indices, I am going to factorize out e to the power of x, which will leave me with a 1. Then this will be e to the power of minus 2x, because when this multiplied by this, I will have e to the power of indices, e to the power of x minus 2x, which is e to the power of minus x. So I have this divided by then e to the power of x, then 1 minus e to the power of minus 2x. In fact, as I'm doing this, I'm suspecting one of my students who is texting me and asking me about one of the questions that I did previously. Okay, I'm not very sure whether you are asking me that question. By the way, if you are one of my students who is texting me like now, you can just WhatsApp me again later. Okay, I'm not very sure what is your question. So e to the power of x, e to the power of x can be cancelled. This I will be left with a 1 minus e to the power of minus 2x over 1 minus e to the power of minus 2. Also, this is a plus, so this should be a plus. So this is plus. Okay, this is going to be my expression for 10x. So let me write it down here. I will definitely use it again. So we know 10x. This is 1 minus e to the power of minus 2x over 1 plus e to the power of minus 2x. Okay, next. We are now given that fn plus 1 minus fn is this. So fn is defined as this in terms of 10, and we are supposed to find Sn, which is the summation of this. What I can observe now is that this expression here is exactly this expression that is here. So I'm going to take this equation and I'm going to make this expression the subject. So which means that for part 2, I am going to write down this shin x of sig m plus half x, then sig m minus half x, and this is given to us as fm plus 1 minus fn, this statement here, which means that sig m plus half x, then multiply by sig m minus half x. This is going to be equal to 1 over shin x of f m plus 1 minus fn, and 1 over this is cosec. So this is going to be cosec x of f m plus 1 minus fn. I'm going to make use of this to try to evaluate this summation Sn, which is equal to the summation of n is equal to 1 all the way until n of this expression here. So it is sig of m plus half x, then sig of m minus half x. So if I were to make use of what I have derived now, x, n is the one that is variable, x is not. So this, I'm going to, when I substitute and replace this by this expression, this, because it is not related to n so far, I'm going to just take it out of the summation notation. So this is going to be cosec x summation of n starting from 1 all the way until n of f m plus 1 minus fn. And what we have here now is one that we have been practicing for, right? This is to be applied, and this is to be evaluated by applying the method of difference. So let's try to rewrite this in the presentation of the method of difference that our school has given us. It is a very, very powerful presentation. It's very simple, but yet it showcases the pattern of cancellation immediately. I'm going to let n be equal to 1. So we have a f2 minus f1. Then when n is equal to 2, let me write down in another row. When n is equal to 2, this is f3 minus f2. Then when n is equal to 3, it is going to be f4 minus f3. And we are starting to see a pattern of cancellation. The pattern of cancellation looks like this. And I'm suspecting that this pattern is going to be translated all the way until the very last part, until the very last term. So in order for me to visually see this pattern of cancellation translated all the way until the last part, I'm going to write down the last two rows. The last two rows will be when n is one term that is before this. So when n is equal to n minus 1, and that will be fn. n minus 1 plus 1, fn, minus fn minus 1, then plus the last term, that is when n is equal to n, that will be fn minus fn plus 1. So fn plus 1 minus fn. And we can see the same pattern of cancellation. And this helps me to imagine, without having to write down everything, that in between here will all disappear. This is the power of pattern recognition. And in case some of my students who is in my weekly class is looking at this, I just want to emphasize to you again, the power of pattern recognition in our class. Next week we are doing something else, but next week onwards, and for the last few weeks that we have been working together, we want to make sure that pattern recognition is one of our most powerful tools. A lot of people will think that pattern recognition is just in summation, which we are just trying to do now, APGP, but it is not. It is happening all over the entire H2 math. We are going to make that as one of our sharpest tools to hit for the A levels. So anyway, let's continue, which means that we have our cosec x. Cosec x, then this will be f of n plus 1, then minus f1. Okay, I guess we are almost there. We are supposed to re-express it into a form that looks like this. And cosec, we already have that here. So now we just need to re-express this into tan, which is expressed as, where fn is expressed as this. So we're going to replace all the n by n plus 1 for this fn plus 1. So cosec x, this, I'm going to replace tan, the n inside here, by n plus 1. So n plus 1 minus half. N plus 1 minus half will be n plus half x. Then minus, I'm going to replace n by 1. So it's going to be tan of 1 minus half is half. So half x. Now comparing this to what I have here, I guess we have gotten the answer. A is equal to n plus half. Okay? The last part. Okay, let me write down the answer here. This A here is n plus half. Let's move on to the last part of part 3. And I think I better shift this up a tiny little bit because apparently my head is covering this part 3. So okay, part 3. Part 3, we want to discuss S infinity to be existing. We explain why S infinity exists. And what we have gotten so far is Sn. Let me just rewrite this again. So Sn is cosec x of tan of A. A is this n plus half x. So A is n plus half, then x, then minus away tan of half x. Okay, so when we talk about S infinity, that is when n tends to infinity. So when n tends to infinity, Looking at the expression that represent Sn, we know that when n tends to infinity, this is the only place where n is affecting. For all the rest, there's no n. So to discuss whether S infinity exists or not, it depends entirely on this part. So I'm going to focus on this. So I'm going to focus on discussion of this, whether S infinity exists, to this tan of n plus half x. And I know what this is because the question has already defined this for us. It is not in our syllabus. The question will tell us some stuff about this, and I guess part 1 is where we have generated an expression that is familiar to us that represent tan x. So I'm going to replace this x by n plus half x. So we have a 1 minus e to the power of minus 2, where x, I'm going to replace it by n plus half x divided by 1 plus e to the power of minus 2 of n plus half x. And when n tends to infinity, that means this tends to infinity, which means that we are looking at unofficially, okay, I'm going to write something that is unofficial. So we are unofficially looking at something that is like e to the power of minus infinity. Okay, because n tends to infinity, this is a negative here. So we are looking at something that is like e to the power of negative infinity. And e to the power of negative infinity will tend to 0, right? Because it's like 1 over e to the power of infinity. So this will tend to 0, which means that this will tend to 1 minus 0 over 1 plus 0, which is equal to 1. So what we have done is to discuss that, okay, when n tends to infinity, since all the rest of the terms are supposed to be finite, and this is also finite 1, therefore I can now say that S infinity exists. Okay, done. And we are supposed to write down S infinity. Okay, we are supposed to write down S infinity, and I guess this is not difficult because we have already deduced that when n tends to infinity, this becomes 1. So S infinity is going to be equal to sec x of this becomes 1. So 1 minus tan, oh, this is tan. So we've had h. So tan of half x. And if I were to compare to this, therefore I can say that P is equal to 1 and Q is equal to half. So let's take a look at this question, question number 6. Question number 6 is a complex number question, and question number 6a, we are supposed to find the roots of this equation, and let's make sure that we recognize precisely the kind of equation that we are dealing with. What we are looking at here is a polynomial. It is a quadratic polynomial. In a way, we should like having quadratic polynomials to be set in our exam, because for all quadratic polynomial, we will be able to solve them pretty easily because we have the quadratic formula. So for this, even for something that is like this, where it is a quadratic polynomial with complex coefficient, we can still use the quadratic formula, and I'm going to just use that. So we have a we have a 1 plus I z squared minus z, then plus 2 minus 2i. This is equal to 0. And I'm going to make use of the quadratic formula. So z is going to be equal to minus b, so negative of negative 1, plus or minus square root of b squared minus 4a c, 2 minus 2i. And this divided by 2a, 2 of 1 plus i. As for this expression within the bracket, my suggestion is you should just simply press the GC, your graphing calculator, because as much as possible, we should try to make use of our graphing calculator. Of course, you can try to evaluate this, to simplify this manually. In the end, you will still be getting a negative 15. For me, I think I don't think it is a very difficult manipulation, so I'm going to just press the calculator for today. In exam, I would definitely want to make sure that I recognize chances for myself to be pressing the calculator. So this is going to be square root of negative 15 divided by this. If I were to expand this a little bit, it is going to be 2 plus 2i. You know why this question is that little bit more interesting? Because although this question didn't explicitly mention that you cannot be, didn't explicitly mention that you cannot be using the calculator, but by setting a quadratic equation with complex coefficient, immediately it is one that we cannot use our Texas Instrument calculator to solve. Our Texas Instrument calculator can solve for polynomials. It can solve all the way until I think polynomial with degree 10, but there is a limitation. Although your graphing calculator can solve for polynomial and give you real or complex roots, but let's make sure that we know that our calculator will not be able to deal with polynomial with complex coefficient. Okay, real coefficient it is possible, but not complex coefficient. That is why, without even having to explicitly mention that you cannot solve this using your calculator, it is just set it in such a way that it is not even possible. So we are using our quadratic formula, and this, I can see this as 1 plus or minus square root of negative 15, square root of negative 1 is I, so we have a square root of 15i, and this divided by 2 plus 2i. Let's rationalize this. So I'm going to break this up into two parts. So I have a 1 minus square root of 15i divided by 2 plus 2i, or another possible answer is 1 plus square root of 15i, and this divided by 2 plus 2i. I'm going to rationalize this first. So we have a 2 minus 2i divided by 2 minus 2i. Okay. As for the denominator, I guess it is simple. The denominator is going to be 2 square plus 2 square. As for the numerator, it will be this multiplied by this, which will give me a 2 minus 2i. Then this multiplied by this minus 2 square root of 15i. This multiplied by this, it is going to give me a minus 2 square root of 15i. So what I'm going to do is to group the numerator into the real portion and the imaginary portion. For the denominator, it's just simply going to be 4 plus 4. So the denominator is 8. For the numerator, if we were to group the real portions together, the real portions will be 2 minus 2 square root of 15. This will be the real portion. And as for the imaginary portion, we have a minus 2 square root of 15. So we have this, and if I were to take this over this, we will have a 2 and 8. They can be simplified. So it will be 1 minus square root of 15 over 4 plus I of this. This is going to be negative 1, negative square root of 15 over 8. Sorry, over 4. Okay. First part of the answer done. We are going to rationalize these two. So this 2 minus 2i divided by 2 minus 2i. Similarly, for the denominator, it is going to be 2 square plus 2 square. And as for the numerator, this multiplied by this, we have a 2 minus 2i, then plus 2 square root of 15i. Then this and this is going to give me a plus 2 square root of 15. Again, regrouping into the real and imaginary portion, we have a 2 and 2 square root of 15. This gives me 2 plus 2 square root of 15 divided by 8. I'm going to just break it up into two parts immediately. So I, and we have this and this. So it's going to be minus 2 plus 2 square root of 15 over 8. So my answer here is going to be 1 plus square root of 15 over 8 plus I of minus 1 plus square root of 15 over, sorry, this is over 4. I have been lacking in, cancelling the 2 and the 8 to get me a 4. Okay, so this is my answer for the first part. I think it is a tedious but quite a good warm-up for us. So 4, done. Next, let's look at B. B is totally not related to A. So let me clean this away. And let's take a look at part B. Part B, we are given f, z. is equal to this, another polynomial. A and B, they are real numbers. This is an important information because if I am dealing with a polynomial with coefficients that are all real, since the question mentioned to me that 1 plus 2i satisfy this, this tells me that 1 plus 2i is a root. And because all the coefficients are real numbers, that is why I know that 1 minus 2i will be another root. I have seen questions before where they actually don't give this piece of information. And we shouldn't be assuming that A and B that are given to us are always going to be real numbers. So let's make sure that we watch out, because if we are not sure that A and B are real number for this polynomial, that means we are not sure also whether this polynomial has coefficients that are all real, which means that it may not be true that if 1 plus 2i is a root, then 1 minus 2i will also be a root. Anyway, now A and B are real. It is given to us by the question. And I know 1 plus 2i is a root of this. So by applying the factor theorem, so if I have fz is equal to 0, and since 1 plus 2i is a root, that means f of 1 plus 2i, this should be equal to 0. So substituting into fz, what we are looking at is 1 plus 2i to the power of 4 minus 2 of 1 plus 2i to the power of 3 plus 1 plus 2i to the power of 2 and a times of 1 plus 2i and plus b, this is equal to 0. And please remember, like what I was saying just now, if you can press the calculator, if you can press your graphing calculator, you should definitely consider pressing it into your graphing calculator. And the reason why I decided to do this substitution is because I know this entire expression over here can be very easily pressed into the calculator, and I will be able to obtain the evaluated result immediately. It is 12 minus 16i from my calculator. So just give me a second. Let me see whether I have some screenshots to show you guys. We are looking at this question number 6. So I have pressed this into the calculator, and just in case you never realize the power of your graphing calculator, this will give me 12 minus 16i immediately. Okay, so let's remember, when we can press the calculator, we should be pressing the calculator. So I've gotten this, then plus this will be a plus 2ai, then plus b, this is equal to 0. And 0, I can also view this as if it is 0 plus 0i. So what I'm going to try to do is to try to match the real portion of the left hand side to the real of the right hand side and the imaginary to imaginary. So let's regroup this. So this is 12 plus a plus b. This is going to be the real portion. And as for the imaginary portion, the portion which has I, we have a 2a minus 16. And this is equal to 0, which is like 0 plus 0i. So matching the real to real, the imaginary to imaginary, I think I'm going to go for the imaginary one first, because it is pretty obvious that by matching this to 0i, so let me just write it here, so plus 0i. So matching this to 0i, I will be able to immediately get my value for A. A is going to be 16 divided by 2, so A is 8. And matching this to 0, we have a 12 plus A, which is 8, plus B, this is equal to 0. This tells me that B over here is going to be equal to minus 20. Okay, now we have our Fz. Let me write it down here. Fz is equal to z to the power of 4 minus 2z to the power of 3 plus z squared plus A is 8. So we have a 8z. BB is minus 20, so this is equal to 0. We are supposed to find the other roots, and we already have one of the roots. In fact, we have two of the roots from our deduction, since the coefficients are all real. So if a complex number is a root, then the conjugate will automatically be also another root, which means we can actually base on these two roots and form the quadratic factor. And this here is supposed to have two quadratic factors. Let me just write this as an expression instead. So this Fz should have two quadratic factor, And if I can find the other quadratic factor, which means that I will be able to find the other two roots. So to find the other quadratic factor, we can do a long division, since I can form the first quadratic factor out of these two roots, or we can also try to make use of comparison. But let's not forget that although all these are possible, but this question didn't actually tell us that we cannot use our graphing calculator. That is why what we should do in order for us to then solve for fz to be equal to 0 is to make use of our graphing calculator. So fz is equal to 0, that means we have z to the power of 4 minus 2z cubed plus z squared plus 8z minus 20 is equal to 0. With all the methods that we have discussed, in the end, the best possible method, and like what we have already talked about since we are looking at question number A, is part A is if we can use our graphing calculator, we should try to use our graphing calculator. And from the calculator, I'm going to get all the possible values for z. Z is going to be equal to 1 minus 2i, 1 plus 2i, which are these two, and the other two will be minus 2 and 2. This is purely from our graphing calculator, and you should be able to get full marks for this. Okay, of course you can go ahead and explore using long division, using comparison, they will work too. But in the exam, under the exam scenario, let's make sure, okay, we grab this opportunity to press the calculator. Next, hence, the question says, after solving this, hence we are supposed to solve for w to the power of 4 minus 2i, w to the power of 3 minus w squared minus 8i w minus 20. This is equal to 0. And I'm really hoping that my students, if you are one of my students in the tuition class, you are watching this now, because we have been talking about a very, very simple and yet pretty useful strategy for us to deal with questions that are like this. I mean, I really hope that you guys are using this, because you know what most people will try to do. I mean, there are some students who were telling me that, hey, this kind of hence question are a little bit more difficult because they can't see what z is going to be replaced by. You know, in order for them to replace z with some compounded expression of w equating to this, then hence find a solution to this polynomial. And I believe that if you are trying to use observation, then you should already know that z is going to be replaced by a compounded expression for w. And one reason, like what I've been talking about in our tuition class, one reason why you cannot see what z is going to be replaced with is probably because you started off with the highest power. I mean, just imagine if z is going to be replaced by a compounded expression of w, and you're going to do a power 4, like for example this, and you're trying to observe when that expression is going to be multiplied by itself 4 times, which means that every time when it is multiplied, it actually makes the observation harder and harder and harder. That is why that one tip that I want to give all of you today, and if you are one of my students in the tuition class, please make sure that you know this, is rather than working with the one that has the highest power, my suggestion to you is you always go for the one that has the lowest power. W, in this case, w to the power of 0, the term that is independent of w. You start comparing and observing from the term that is independent of w, then you go towards the higher powers. So this minus 20, nice, they are the same, which means that I probably don't have to manipulate this equation much. And so minus 20, I'm going to retain. Let's work from the lowest power. Okay, this is a very, very good strategy. And I believe that z is going to be replaced by a compounded expression in terms of w. So what if I were to rewrite this as plus 8, the coefficient plus 8? And what is that compounded expression of w, so that this will give you minus 8iw? It will be minus iw. Okay, so my suspicion is that z is going to be replaced by minus iw. I mean, I think it is pretty easy to see that z is going to be replaced by minus iw, right? So what if this is going to be true also? So it should be plus then minus iw square. If z is going to be replaced by minus iw, let's verify. Minus I square is going to give us a minus 1. W square is going to be w square. So nice, still correct. So this, I suspect it is going to be minus 2. Then z is going to be replaced by minus iw. So this to the power of 3. Minus I to the power of 3 is I, and W to the power of 3 is W to the power of 3. I am still correct. And lastly, now we come to the highest power of W, which is W to the power of 4. And if Z is once again replaced by minus IW. And minus IW to the power of 4, minus I to the power of 4 is 1. W to the power of 4 is W to the power of 4. Okay, so this is totally, I mean, this is way easier the moment when we start to work with the smallest power. Okay, a very, very good and useful strategy for our exam. That means, looking at the answers here, minus IW is going to be equal to minus 2I or 1 plus 2I or minus 2 or 2, which means that W here is going to be equal to 1 minus 2I divided by minus I, 1 plus 2I divided by minus I, this is I. So, and minus 2 divided by minus I, and 2 divided by minus I. So W here is going to be this divided by this will give me, using my calculator, it is going to be 2 plus I, and here we will have a minus 2 plus I, and minus 2I and 2I. I see a very interesting question here. Okay, can I answer this question? Is it solving usable? Okay. Okay, one of you who wants to remain anonymous has asked that, is it solved using polynomial from polynomial function on the calculator? Yes. If you are trying to solve this, you're going to use apps, then polynomial simultaneous equation, then solve. Okay, but just now, in case you have just joined us, we need to know that our calculator can solve for polynomial, but it has a limitation. Our calculator can only solve for polynomials with real coefficient. So for example, this, yes, my calculator can solve for me, and it's going to give me 4 solutions, which was what I did after I have found A and B. Apps on your Texas Instrument calculator, apps, polynomial simultaneous equation, then polynomial root finder. But this is not possible. Okay, for a polynomial that looks like this, because the coefficient has complex number, so we will not be able to use our graphing calculator to solve. And that is why I do appreciate the way this question number, this part A, is very subtly set in a way that they didn't have to explicitly mention that you cannot use a calculator, but by making sure that the coefficients are complex numbers, then you just cannot use a calculator anymore. Okay. Okay, let's continue. Oh, wow, actually we have already solved for question number 6. Nice, good timing. Let's continue to question number 7. Let's take a look at 7. So question number 7, let me find question number 7 on my whiteboard here. Question number 6 and question number 7. Question number 7 looks a little bit intimidating with all this I, N and stuff, but I don't think it is as intimidating as the question number 5 that I did with some of you on Tuesday, right? Question number 5 just looks, wow. You know, when you look at it, you just feel like, you know, I'm halfway through and I'm looking at a question that is like this. What if the next few questions are all looking like question number 5? But as we did it, it was pretty okay, isn't it? So let's hope that, not hope, you know, let's have a little bit of confidence in looking at question that is like 7. To do question number 7 well, I do think that you definitely need to use graphing calculator because the question. Yeah, actually someone asked a question. You know, in our Cambridge exam, one of the learning point in that is mentioned in your instruction, right? I mean, in when you're signing up for the exam, is actually students must exhibit, you know, the ability to make use of the equipment and the device extremely well. So there will be a lot of chance for you to use the graphing calculator. In fact, by default, as long as the question didn't say that you cannot use the calculator, you should be using the calculator. That is why in question number 6, at a lot of times, we will be exercising, making use of our graphing calculator. And like what I was telling you, I don't think there are, I don't think everyone has already known by now that your calculator cannot solve for polynomial with complex coefficient. And that is why we should be exploring our calculator, so that just in case we actually need to use it, and or if there's a chance for me to use it, we should try to make use of it, and we are going to be getting the marks, and we don't need to waste time doing all the manual work. Okay. Question number 7. It is an integration question, but for this question, you do need a little bit of, you do need to study the concept of how you can be making use of rectangles to approximate area under the graph. Okay, this is an area under the graph scenario. The area A represents the region that is bounded by this curve and this and this. So if I were to do a quick sketch of this on my graphing calculator, I'm going to get something that is like this. Okay, let me sketch it out for you. So I'm going to be getting something that is like this. If this is the y-axis, if this here is the x-axis. So the graph will start from here, and then it will end at somewhere that is like this. It is going to be bigger or equal to 0. It can be equal to 0, so I'm using a solid dot, and it can be less than or equal to pi over 2. When it is at 0, it is at the origin, and when it is at pi over 2, sine of pi over 2 is 1. 1 to the power 6 is still going to be 1. So I have this, which means that here is going to be equal to pi over 2. And according to the question, we are supposed to approximate this by dividing this into 5 equal width rectangles. And the way that we divide the rectangles can be done in 2 ways. And that is why it is possible for a question to ask us without having to explain more than, without having to go into the details. Why is it possible for us to deduce the A is between 2 values if we were to be looking from the perspective of making use of rectangles to approximate area under the graph? Because the 2 ways that we can draw the rectangles, if you were to look at the theory outlines that I have on Achevas TV, the first way is an over approximation, then an under approximation. An over approximation scenario will be like this. From here to here, I'm going to be chopping up it into 5 equal width rectangles. So let's say here 1, 2, 3, 4, 5. So the first way that I can draw the smallest possible rectangle that can approximate this, not the smallest possible, but a possible good enough, a good enough approximation using a rectangle is probably to go all the way, then here. Okay, this can be one of the rectangles, and the second rectangle, it will be this, then all the way. Wait, I need a consistency, so I'm drawing with a certain kind of pattern, so I believe that you can see this pattern. But anyway, this question should be studied before you are able to attempt this. This concept should be studied before you are able to attempt this question well. So if you realize that you are not very well versed with this, please make sure that you go and take a look, check out the videos that is on Achevas TV. I will be explaining this also. It is under the theory outline for areas and volume. Okay, so looking at this, I know that they are equally divided. So 0 to pi over 2 divided by 5, it will be pi over 2 divided by 5. That will give me a pi over 10. So this will be the x coordinate, which will also be the width of every single rectangle here. So plus another pi over 10, we have a 2 pi over 10. Then this will be a 3 pi over 10. Then here we have a 4 pi over 10. Then 5 pi over 10, which is going to be pi over 2. So the areas of the area of the rectangles that we are seeing here, it is going to be width, base times height. So the base is pi over 10, and the height will be the y coordinate of this point. And the y coordinate of this point can be obtained by substituting this back into the original curve. The curve of y is equal to sine to the power of 6x. So replacing x by this, the height of this first rectangle will be sine to the power of 6. Let me just write it as sine to the power of 6. So we have a sine to the power of 6 of pi over 10. And for the second rectangle, the width is once again pi over 10. And as for the height, it is going to be sine to the power of 6 of the y coordinate of this point, which is going to be substituting this into this to get a y coordinate. So sine to the power of 6 of 2 pi over 10. Then another width, which is pi over 10. Then sine to the power of 6 of 3 pi over 10. And this, it is going to be plus pi over 10 again. Then sine to the power of 6 of, we have already done this. So this, this. So this is going to be equal to 4 pi over 10. And for the last rectangle, it will be pi over 10 sine to the power of 6 of this substituted in, it is pi over 2. Then I'm going to press into my calculator. From my calculator, this is going to be equal to 0.20625 pi. Nice, because it is this number over here. Sketch when finding the areas of the region. When can we use endpoints here? Okay, I see some questions, but let me just continue with this first. So anyway, let me continue. Okay, so this is the first way that I can be sketching the rectangle. There's another way for me to sketch the rectangles, which is going to give me an under approximation. So the second way, let me sketch it here. So if I were to draw my graph here and here, so my graph is going to be this all the way until here. So I will sketch an endpoint here and an endpoint here. This endpoint is going to be 0. This endpoint that I'm looking at, it is going to be pi over 2 and 1. There is this question which I am not very sure about why. This question says, why can you use endpoints here? I mean, to me, why can't I use endpoint here, right? Because if you were to be looking at, I'm trying to analyze the graph from 0 to pi over 2. So of course you can draw and continue with the entire graph, but if I'm looking at just to be between 0 to pi over 2, then I want my graph to stop here and it can be equal to this, or else I will not be able to substitute pi over 2 into x. And I'm going to let this be also an endpoint. That is why I can substitute pi over 2 into x. Okay, that is why it is my decision to use an endpoint, but of course it is also possible for you to continue. I don't think there's any problem using endpoints here. In fact, in my tuition class, we were talking about endpoints, that it is a very strategic thing that we can try to apply to our H2 math. It can actually help us to score marks in the exam. Okay, anyway, let's focus on this question. So another way for me to be drawing the rectangles, instead of drawing it above the curve, we can actually draw it below the curve. So for example, if I were to draw the first, here is going to be equal to pi over 2. So if I were to again break this up into 5 parts, it will be like this: 1, 2, 3. Oh, ugly, but okay, you get it, right? It is supposed to be 5 equal parts. Okay, so now I'm going to try to sketch it below the curve instead of above the curve. And the reason why I am doing this, because the question is actually asking me for something that require me to have a prior knowledge of how the rectangles can be sketched. If I were to be sketching it above, then I will be definitely getting an area that is more than A. A is the exact area. So I will probably be getting this value, which I did. And if I can sketch it below, then I will be, when I sum up the areas of all the rectangles, I will be getting a number that is less than A. And that should give me this number. Okay, that is why I was saying that this question requires us to study H2 math properly first. Okay, because we cannot deduce this just by looking at the two numbers here. We need to deduce this based on the concept. So we have 5 rectangles with the first rectangle as like totally flat on the x-axis, so the area is 0. So now if I were to calculate the area of the rectangles for this case, then it is going to be the first rectangle, it is 0. The width of the rectangle, it is still going to be pi over 10. So for the second rectangle, the height is going to be dependent on the y coordinate of this, which is to once again substitute pi over 10 into sine to the power of 6x. So it will be width pi over 10, and the height will be this. So it will be sine to the power of 6 of pi over 10 plus another rectangle. So the width here is going to be equal to pi over 10 also. The height is this, and it depends on 2 pi over 10. It's called pi over 10 plus pi over 10. So this will be sine to the power of 6 of 2 pi over 10. Then the next rectangle, so this done. The next rectangle, the width is pi over 10. And as for the height, it is going to be the y coordinate of this. I'm going to be using 3 pi over 10. So I am substituting 3 pi over 10 into this entire thing, which is sine to the power of 6 of 3 pi over 10. So this rectangle done, we have one last rectangle. So this plus pi over 10. Then for this one last rectangle, this 3 pi over 10 plus pi over 10, this is 4 pi over 10. So we have a sine to the power of 6 of 4 pi over 10 as the height of the last rectangle. And pressing this into the calculator, nice, it is going to be 0.10625 pi. And since we are talking about the area as A as the exact area under the curve based on our observation from these two, we know A is going to be between 0.10625 pi and 0.20625 pi. Okay, so we have this done. Where prior knowledge is necessary for me to execute part 1 well. And this came out in the A-level recently, so please make sure that you study this properly, especially when A-level is setting it, especially when A-level set it a few years ago, they set it based on this prior knowledge. So you really can't just read the question and then try to react according to the question. Next, let's look at part 2. Part 2 is actually very, very interesting. Let's see what part 2 is trying to ask us to do. So part 2. Part 2, we are given that In is equal to this. And by rewriting this into this form, we are supposed to get, we are supposed to be getting this, which means that we will probably be starting with In. So we have In here. So In, we know it is going to be equal to this. So we will probably be starting with this, integrating from 0 to pi over 2 of sine of 2n x dx. Okay? So we have this. And according to what the question says, we are supposed to break this up into two parts. So let's just do what the question asks us to do first. So integrating from 0 to pi over 2 of this, and I'm going to break it up into two parts, which is going to be sine x multiplied by sine of 2n minus 1 x dx. Okay? And before we continue, let's just take a bearing of what we are trying to look at here, because I'm definitely going to be integrating this, but I'll not be expecting something that is like this according to the experiences that we have doing other questions, right? So let's take a look at what exactly we are supposed to obtain as we continue to try to integrate this. So I would suggest that you pause for a little bit, as we are doing this question, pause for a little bit. I know in the end, I'm supposed to be getting this. So this is supposed to be 2n minus 1 divided by 2n of in minus 1. So in is this. What is in minus 1? It is going to be integrating from 0 to pi over 2 of sine of 2n minus 1 x dx. And this is wrong. And I think there will be some people who will be writing in minus 1 in this form, where this is probably a painful mistake to make in the exam. Because once you cannot get this, most likely you will not be able to do the next few parts well. What is wrong with this? What we are trying to do is to replace n by n minus 1. It is not just simply take 2n minus 1 like this case. So this is baseless. What we are going to do is to make sure that we apply our notations well, replacing n by n minus 1. So 2 replacing this n by n minus 1. We have this x dx. So whatever that we are trying to do, we are trying to show that it can take up a form that is like this. So let us see whether we can do that. And I believe that for a question that is like this, a very high chance, actually it's not, I believe. The question has actually told us that we are supposed to do this by integration by parts. So one of it has to be u and the other has to be dv dx. This is not going to be the kind of question that I can apply LIATE. So we probably should try to make decision based on, to me, integration. Because not everything is that easily integratable, but most expression that is in our syllabus can be differentiated. So comparing sine x and sine to the power of 2n minus 1x, I will say that this is the one that is definitely differentiable, but I cannot integrate this. Okay, that is why I am going to let dv dx be sine x. Because if I were to let dv dx be this, it is basically like I will be stuck, right? So I'm going to go for u to be this sine of 2n minus 1x. So from here, we will find du dx. Du dx will be 2n minus 1 and sine to the power of 2n minus 2x. Quotient rule, so I got to, chain rule, so I got to differentiate sine x, and that will give me a cosine x. And I will be integrating this, which means that v integrating sine x, this is going to be minus cosine x. Okay, now we have prepared the terms that I need for integration by parts. So this is going to be equal to uv. So it is going to be sine of 2n minus 1x times this. I'm going to put a negative in front, then cosine x from 0 all the way until pi over 2. Then minus integration of v du dx. So v du dx. So it's going to be this multiplied by this. So this multiplied by this, we will have a minus 2n minus 1 sine to the power of 2n minus 2x. This times this gives me a cosine square x. Okay, now we have this dx. Okay. I think this can be taken out. And the nice thing is 2n minus 1 is actually here. So it seems like we are on the right track. So let me substitute the lower and upper limits in. When I substitute this in, cosine of pi over 2 is 0. And when I substitute this in, sine of any power of 0, it is going to be 0. So this, when I do the substitution, it is going to be 0. I'm going to factorize this out, and I'm going to be getting this 2n minus 1. So it will be plus of 2n minus 1 integrating from 0 to pi over 2. I shouldn't forget this. So from 0 to pi over 2 of sine of 2n minus 2x. Actually, sine of 2n minus 2 is just this, right? This is 2n minus 2 as the power. So it does seem like we are getting somewhere there, but there's this cosine square, which I think I'm going to rewrite it as 1 minus sine squared by making use of trigonometric identity. So this x dx. And for some of you who are watching this, especially those of you who are watching on YouTube, we are doing the Singapore A-level paper that is actually set by a school, River Valley High School in Singapore, which is in preparation for our students here in Singapore to be taking their A-levels. So now we have 2n minus 1. I think what I'm going to do is I'm going to multiply this in, which will then give me integration from 0 to pi over 2. This multiplied by 1, we have a sine of 2n minus 2x dx. Then this and this, it is going to be minus integration from 0 to pi over 2 of This multiplied by this is going to give me a sine of 2n, then dx. And this is actually the same as this. It is exactly the same as this. So I am going to rewrite this as 2n minus 1 of this is this, which is in minus 1. Okay, we have already decided this from here. So this is actually in minus 1, correct? And minus this, which is in. So we have this in. And this is in. So I am going to regroup this, which will give me a in, then equal to 2n minus 1 of in minus 2n minus 1 of this in minus 1. I'm going to bring this over to the left hand side. So I have a in, then plus 2n minus 1 of in. This is equal to 2n minus 1 of in minus 1. We are extremely close to this already. I just need to combine this, which will give me a 2n of in. This is equal to 2n minus 1 of in minus 1. And now we have gotten it. In is equal to 2n minus 1 divided by 2n of in minus 1 shown. Nice question. It is one where we have where we are doing integration, but yet we are applying a little bit of notation. So now we have proven this, and we are going to try to prove this. Oh, actually, right? You know, I see a mistake. I mean, not a mistake. You know, Joven, you're asking why can't we integrate this to the power of 2n minus 1 x dx. How are you going to integrate this? This is not x to the power of 2n minus 1. So it is not like integrating this where we are going to like this to the power plus, I mean this plus 1 then divided by plus 1. It is not. This is sine to the power of. Okay, so we cannot. It's just like, can we immediately integrate sine to the power of 6x? We can't. Okay, so this is very difficult to integrate. So we cannot, okay, we just cannot be integrating this. Or maybe Joven, you can, this is going to be your homework, okay? Go and try to integrate this. Claire is saying that we should be integrating the easier part. I don't exactly agree with you, Claire, because right, yes, we are going to be integrating the easier part, but this is almost like what Joven was asking. This is almost impossible to integrate in our syllabus. So it is not me choosing the one that is easier. It is me choosing the one that can be integrated, because the other one is just going to be impossible for us to be integrating within our syllabus. Okay, anyway, let's continue. There's a, I really want to do this real value question, okay, but I should go and do a check, because I keep hearing people saying anyways, you know, like why is there anyways with an S? So I'm going to check it out. Maybe it is cooler for me to say anyways. Let's continue with this. So we are going to find I2, and let's not forget what is IN, and let's not forget what is IN in terms of IN minus 1. So what the question is trying to say now, is definitely about making use of this. So n is equal to 2. So this is equal to 2 times 2 minus 1 divided by 2 times 2. Then I of 2 minus 1 is 1. So I 1. So we are getting a 3 over 4 of I1. What is I1? Okay, it is replacing n by 1. So sine square we can integrate, but we need to re-express sine square as double angle formula before we can do our integration. It is not like we can integrate it directly, okay? So because we cannot integrate this directly, or else the question wouldn't have asked us to re-express this into this, then doing integration by parts, we would have already started integrating from the very beginning. But before you start to integrate I1, I can actually apply this to I1 again. Why? Because n for this is supposed to be bigger or equal to 1. So it is applicable to when n is equal to 1. So that will be 2 of 1 minus 1 divided by 2 of times 1 of I1 minus 1 is 0. So now we have a 1 over 2 of I0. And what is I0? For I0, I'm going to make use of this. Can I make use of this? Yes, I can. Why? Because n in this case starts from 0. So it is possible for me to make use of this to be applied for I0, and this is going to be half of integration of 0 all the way until 2 pi over 2 of sine to the power of 0, anything to the power of 0 is 1, then dx. So this is going to be just half of x, integrating this from 0 to pi over 2, and this is just going to be half of pi over 2, and this is pi over 4. So I know this is now going to be equal to 3 pi over 2 multiplied by pi over 4. Now we have gotten our answer 3 over 16 pi. Okay, done. And we are going to try to make use of this I2 to obtain the exact value for A. And let's check out again what is A. A is the exact area under the graph. So the exact area under the graph using integration, it is going to be integrating from 0 to pi over 2 of sine to the power of 6x dx. And I need to reference this back to this in order for me to make use of whatever that we have found now, especially I'm looking at an I2. So I need to see an I2 within here. So this is going to be integrating from 0 all the way until pi over 2. This, I will see this as 2n, which is 2 times of 3x dx, which tells me that this is I3. And what is I3? Making use of this, it is 2 times of 3 minus 1 divided by 2 times 3 of I2. So it is going to be 5 over 6 multiplied by I2. I2 is 3 over 16 pi, which we have found in the previous part. And now this is equal to 5 over 32 pi. A very, very nicely set question with all the details that are really thought of by the teachers who is setting this. Rio Valley, it's a good school. So anyways, okay, question number 7, let's move on to question number 8. I see this question here. How can we use I0 since the range of n is more or equal to? Okay, for this question that is asked, when I go for I0, I went for this, and this allows n to be equal to 0. And when I went for I, for example, I2 is equal to 2 times 2 minus 1 divided by 2 times 2, I1. When I apply this, I went for this, and this is when n is bigger or equal to 1. That is why even for this I1, what is I1 in this equation? That is when n is equal to 1. So this is 2 times 1 minus 1 divided by 2 times 1, I0. But I can't apply this for I0 because this is only for when n is bigger or equal to 1. So for I0, that is the minimum I can go. And the next thing that I can do is to reference I0 back into the actual integration. Okay, that is why I do feel that this is a very nicely set question because a lot of details are taken care of by the teachers. When I was saying last week that because I was from River Valley when I was in my secondary school, that's why I'm proud that I see a question that is of this kind of level from River Valley. So anyways, let's look at question number 8. 8 is a vectors question. Actually, this question is pretty okay. where I don't find this question particularly difficult. Let's try to do this a little bit quicker. I have P1 and P2, they are given to me in the Cartesian form. Let me just rewrite P1 and P2 in the dot product form. I think it is definitely more useful in general for vectors. So P1, I know I can rewrite it into dot product form as R dot 154. This is equal to 4. And as for P2, this will be R dot 1 minus 1, 1. This is equal to 4. Explain why P1 and P2 intersect in a line L. So for part 1, my explanation will be since P1 is not parallel to P2. Since they are not parallel to each other, that means they are going to be intersecting. How do I see that they are not parallel to each other? We can just simply look from the normal. If the normals are parallel to each other, then the two planes must be parallel to each other. And any two planes that are not parallel to each other will definitely be intersecting, and they will be intersecting at a line. Okay, that's why since these two planes are not parallel to each other, they are intersecting at a line, and we are going to call that line L. And we are going to try to determine the Cartesian equation of this line L. And let's make use of our graphing calculator. Okay, I mean, I see a question, but I'm not very sure what this question is for. It should be in Cartesian, right? Okay, I am really not very sure what this is. I'm going to just archive this question for now, okay? Let's continue first, then maybe along the way, whatever that you're asking will be sorted out. So for this question number 6, I'm going to press this into the calculator. Okay, I'm going to stick to the planes in the Cartesian form. Then I'll press these two into the calculator. Again, apps, polynomial simultaneous equation solver. I'm going to be choosing 2 equations with 3 unknowns. So with the 2 equations and 3 unknowns pressing into the calculator, this is a set of solution that we have gotten. We need to know how to decipher this solution from our graphing calculator. So from what we should have learned, if you have not, please again check out what we have on our in the theory outline on the Achevas TV. So this, I know x1, if I were to be pressing this in the calculator, will represent x. So x is going to be equal to 4 minus 3 over 2z. Then y is equal to 0. I'm not going to write it. So half z, and z is equal to z. We want to rewrite the equation of this line in the Cartesian form. So one way is to immediately let z be the parameter that's going to be defining my vector equation later on. So maybe I'm going to let that parameter be, let's say, I don't know, let's say lambda. Okay, so I'll let this be lambda. So I have x is equal to this. I'm going to make lambda the subject. Okay, and the reason why I am doing this is because I am writing I'm planning to rewrite this. I'm planning to give my solution to the equation of this line in the Cartesian form. So I'm going to make lambda the subject. I'm going to multiply throughout by minus 2. So minus 2 is equal to minus 8 plus 3 lambda. So lambda here is going to be, minus 2x. So lambda here is going to be 8 minus 2x divided by 3. As for this, lambda is just going to be minus 2y, and lambda is already z. So lambda is this, 8 minus 2x over 3. Lambda is this, which means that this is going to be equal to minus 2y, and lambda is this, so this is equal to z. This is my equation of the line L in the Cartesian form. We are going to be using L quite a fair bit. We're going to be using L here. We're going to be looking at L again. And okay, here I don't think we'll be making use of L. Maybe we will. But the thing is, L is just not going to be as efficient if we were to stick to the Cartesian form. So let's try to rewrite L in the vector form. I do think that is way more efficient. And why did I even delete this? I will still want to have this. So coming back to this again, we have x is equal to this, y is equal to this, z is equal to this. So we have this. I'm going to just rewrite this, okay? So x is equal to, if I were to rewrite this in the column vector form, so x y, z. Based on what I have here, which I try to reinterpret into this way, this is going to be 4 minus 3 over 2 lambda and minus half lambda and lambda. And this, I'm going to re-express it as r. So r is equal to 400 plus, if I were to take out lambda, I will have this minus 3 over 2 minus half and 1. And I think it will be easier if I were to factorize out minus half. So I'm going to go for 400, then minus half lambda of 3, 1, and minus 2. Okay, and this I'm going to just simply call it as another variable. So it will be 400 plus, let's say, mu. So mu is equal to minus half lambda of 3, 1 minus 2. This is going to be the more useful version of the equation of L instead of this. I'm going to just write it down here. So I know L is this R is equal to 400 plus mu of 3, 1 minus 2. Okay. Next. Next, part 2. Part 2, P3. It contains L and it contains this point. I want to find the Cartesian equation of P3. So we have a scenario that is something like this. So let's say this is my P3. So let's say this is my P3, and if I were to draw the line L here, so this line is L, and for the line L, it contains this point and it is parallel to 3, 1 minus 2. So this point that it contains, I'm going to call this point T. Just in case you were wondering, of all the letters, why do I use T? Because I realized that T later in part 3 is 400. So I might as well just indicate this point T that is on P3, and this line is going to be parallel to the vector 3, 1 minus 2. And this plane contains the point Q. And Q has a coordinate of 5, 3, and minus 6. So if I were to join this to this, QT should be parallel to P3. And I have another vector that is also parallel to P3 because this 3, 1 minus 2, which is parallel to L, and since L lies on P3, 3, 1 minus 2 should be parallel to P3. So what I'm planning to do is to get this vector, and I'll cross this vector to get for myself the normal vector. So this is going to be OT minus OQ. So it will be 400 minus 5, 3 minus 6. This is going to get me a minus 1, minus 3, 6. And to get a normal vector, minus 1, minus 3, 6, cross this 3, 1, minus 2. And I'm hoping that you guys are trying to do the question together with me. I don't think I'm going like at a very, very fast pace because I'm still talking a little bit. So it gives us a little bit of chance to, pace ourselves a bit. I don't. Okay, anyway, let's just continue, okay? But please try to do the question together with me if it is possible. I think it is going to be a good experience if we can try to work on questions together every week. So this, if I were to do the cross product, covering up this, I'll take this, multiply by this, minus this. So I have a 6 minus 6, it is going to give me a 0. Covering up the second row, I will have 6 times 3, 18, 18 minus 2. This is going to be equal to 16. Covering up the third row, it will be minus 1, minus, so it will be plus. Minus 1 plus 9, this is going to be equal to 8. So I have this, which I can also rewrite it as 8 of 0 to 1. Because we need a normal vector. In fact, we need any vector that is perpendicular to P3, 0, 16, 8 is perpendicular to P3, 0 to 1 is also going to be perpendicular to P3. So for P3, the equation will be r dot 0 to 1 is equal to, I'm going to take a point that is on P3, let's just go for the point T. So it has a position vector of 400 dot 0 to 1. This is going to be equal to 0. And if you are able to, it is not exactly asked by the question, but if you are able to, do recognize that a plane that is like this, r dot the normal is equal to 0, is going to be a plane that passes through the origin. Obviously, because the origin 0, 0, 0, when it is substituted to replace r, 0, 0, 0 dot this is going to be 0. So the position vector of the origin satisfy P3's equation. That is why P3 should pass through the origin. So now we know P3. Let me write it down here. P3 we are supposed to write it in the Cartesian form. I don't think that is very difficult. So I'm going to replace r by x, y, z. So this dot 0 to 1, this is equal to 0. So I have a 2y plus z. This is equal to 0. P3 in the Cartesian form. But I'm going to retain the dot product form. It is definitely going to be more useful for us. So this is equal to 0. Let's move on to part 3. Part 3 is pretty standard to begin with. It ends off with a line of reflection, which on the Achevas TV theory outline, in the very last page and at the most bottom right portion of the theory outline for vectors, I talk about reflection of geometries about another geometry. Okay, it is a very detailed discussion, and the reason is because reflection is going to be the kind of questions that's going to be appearing in our exam. We don't have to wait till the exam to try to react to a reflection question. So please try to study all the reflection stuff before you even go into the exam. And especially when reflection is usually going to carry a lot of marks. So we have this line M that passes through S and passes through T. We want to find the position vector of the foot of the perpendicular from point S, which is 0 to 0 to P2. I don't mind talking about this because P3 is this, right? So if P3 is this, when this is equal to 0, one thing that we can deduce, it is not about this question, okay, but one thing that we can deduce is that 0, 0, 0, if I were to substitute to replace this r, this dot 0 to 1 is definitely going to be equal to 0. That's why 0, 0, 0 satisfy this equation, and that immediately can help us to deduce that the origin should fall on P3. It is a useful information to have. I mean, it is not exactly that useful for this particular question, but in case it is asked in any other question, at least we are able to spot P3. What is the distance between P3 to the origin? 0. There is this part 3. Someone is saying that I have missed out the last part of part 2, finding the Cartesian equation of P3. Okay, I guess just now I've already written down the Cartesian equation of P3. It is 2y plus z is equal to 0. We're replacing all the r by x, y, z. Okay, we are supposed to find the position vector of the foot of the perpendicular from S to P2. So we are trying to find this point here. I'm going to call this point here N. We have a strategy, and again, the strategy has already been discussed on the Achevas TV outline. On the very last page of the outline, we talk about the foot of the perpendicular from S to from a point to a plane. It is a very good strategy. It is not the only way for us to find foot of the perpendicular, but vectors. After we have studied all the concepts for vectors, the next phase is actually consolidating and accumulating as much strategies as possible to execute during the exam. So I'm going to execute a strategy that I've discussed on the Achevas TV outline, which is to form a line that passes through N and S. This line that passes through N and S is going to carry the point S. So here it will be 0 to 0, then plus, let me go for another variable. beta of a direction that is going to be parallel to P and S, and P2, where this P and S is perpendicular to, has a normal of 1 minus 1, 1. That is why this NS will also be parallel to 1 minus 1, 1. So here I'm going to go for 1 minus 1, 1. And since point N lies on this line, and this represents the position vector of any point that is on the line, so I can say that ON should take up a form that is similar to this. So this is going to be equal to beta, then 2 minus beta and beta. Okay, ON is this. So ON is this, and N is also a point that lies on P2. And P2's equation is this, which means that the position vector of N should satisfy this, like what we have just discussed here. So ON should satisfy this equation. So this dot 1 minus 1, 1, this is equal to 4. So we have a beta 2 minus beta, beta dot 1 minus 1, 1, this is equal to 4. So we have a beta minus 2 plus beta, this is equal to 4. This will help me to solve for beta. Beta is going to be equal to 2, which means that ON, the foot of the perpendicular, this is equal to, when beta is 2, it is going to be 2, 0, 2. So this point here is 2, 0, 2. The foot of the perpendicular from S to P2. Oh, okay. Thanks to Alvin, there's indeed this one last part that I've forgotten. Describe the geometrical relationship between the three planes and L, because I know P1 and P2 intersects at L, and since P3 also contains the line L, that means all the three planes are supposed to be intersecting at a common line, and that common line is L. Okay, it is for this part. So now we have the foot of the perpendicular, and we want to find the reflection of the line M in P2. We want to find the reflection of the line M in P2, and M contains S and M contains T. And where is the point T? The point T, 4, 0, 0, is on L, and L is on P2, since L is the intersection between P1 and P2, which means that the point T, let's say it is here, the point T 4, 0, 0 lies on P2, so this is going to be M. Like what I was saying, vectors is about, a large part of vectors is about studying a strategy to execute when you see the moment is right. So we have a few strategies. One of them is, like what I was saying just now, finding a reflection. So I'm going to continue to use the strategy that we have discussed in our theory outline on Achevas TV. And from here, if I were to talk about a reflection, and I'm going to call this M prime. We have a piece of information of M prime already, because M prime passes through the point T. The next thing that we want to do is to find another point that is on M prime, which is the reflection of M. And that's what the question asks for, the equation of the line M prime. So what I'm going to do is I am going to find the reflection of the point S about P2, because the reflection of S about P2 should be lying on M prime. And I'm going to call this point M prime. And this reflection, if I were to draw a line from here to here, should pass through N. And in fact, because it's a reflection, so this is going to be equal to this, which means that the proportion is going to be 1:1. And I'm going to reference all this to, let's say, the origin, which is, now we know it lies on P3. So but it doesn't really matter for this. So if I were to reference all this to the origin, what we can try to do is to apply the ratio theorem. Applying the ratio theorem, I know ON is going to be equal to 1 time of OS plus 1 time of OS prime. This divided by 1 plus 1. And we are supposed to find OS prime, because once I've gotten this and with this, we should be able to find the equation of M prime. So OS prime, making this the subject, 2 multiply across 2 ON minus away OS. So it will be 2 ON is 202 minus OS 020. So OS prime, this is going to be equal to OS prime, this is equal to, I could have just done my mental sum. So this is going to be, this is this 4, then minus 2, then this is going to be equal to 4. So I have OS prime as this, and the next thing that I'm going to do is to find the vector that go from here to here. So let's go for S prime t. So S prime t will be 400 minus away 4 minus 2 4, and this is equal to 02 minus 4. And since when I try to find S prime t, my aim is to get a direction that is parallel to M prime. So if I were to factorize out 2 from here, 0, 1, minus 2, I'm going to just use this as a direction that is parallel to M prime. That is why M prime is R is equal to the position vector of any point. I'm going to use point T, so 400 plus, let's say gamma of 0, 1, minus 2. Okay. Next, let's look at question number 9. Question number 9. Question number 9, let's see. Okay. APGP, right? This is an APGP question. So for this question number 9, oh no, what's happening? For this question number 9, Mr. Tan, he starts saving on the 1st of January 2019. Initially, he deposited $5,000. The bank offered a compound interest of 1%, and it is going to be awarded at the end of each month. And Mr. Tan is going to be withdrawing $100 from the account at the beginning of each month, and that will only start in February. Part 1, we want to calculate the amount of money that is in Mr. Tan's account by the end of March 2019. Let me build for myself a table to try to quote, the way that the money is being compounded. So if I were to go for the month, and I am going to be looking at the total amount of money that is in his saving account at the end of the month. Okay, I'm working on the end of the month. So for the first month, and that is in January. So by the end of January, Mr. Tan will initially put in $5,000, and by the end of January, it is going to be compounded by 1%, so I'll multiply this by 1.01. Then February, which is the second month. So in the beginning of February, this will be the amount. And then Mr. Tan is going to be withdrawing $100. So minus 100, and by the end of the month, this is going to be compounded by 1%. So we are seeing this as 5,000, 1.01 square minus 100, 1.01. Then March, which is what we are trying to calculate. So for the month of March, in the beginning of March, Mr. Tan will have this minus 100, then 1.01, minus away 100 again because he's withdrawing $100 in the beginning of the month. And then this is going to be compounded, so 1.01. We're going to be calculating this, but let me reorganize the information even more. So we have a 5,000 then 1.01 to the power of 3. Oh, much, this 3. Then all these negative, I'm going to consolidate them also. So it will be negative of this times this. It is 100 of 1.01, then plus 100 of 1.01 square. That is going to be from here. So I have this. I'm going to press this into the calculator since the question is asking me for the amount at the end of March. And from my calculator, this is going to give me a 4948.50. And part 2. Part 2, we are supposed to deduce the amount of money in his account at the end of the nth month. We have already done 3 months. In fact, because of the way that we have organized this, I think it is not difficult for us to deduce from this point onwards the nth month, 1, 2, 3, then nth. But I do think it is a slightly better habit, especially if I were to be doing this during the A level. I will probably write down the 4th month. And the reason is because I'm suspecting that this is going to be a GP with the first term as this, and the common ratio is 1.01. It is pretty obvious because after writing down 1, 2, and then 3, I can already see that the pattern is going to continue. But it is always better when I try to deduce whether something is an AP or GP to have at least 3 terms, right? Because when 2 terms, I mean this divided by this is a number, it doesn't mean that it is a GP, but if I have 3 terms, then at least this divided by this, if it's the same as this divided by this, I know it is going to be a GP with a common ratio. So I'm going to continue to write down for the 4th month, April. And it will be starting with this 1.01 to the power of 3 minus away 100 1.01 plus 100 1.01 square. Then Mr. Tan is going to withdraw $100 and the bank is going to give a compounded interest of 1%. So this is equal to 5,000, then 1.01 to the power of 4 minus away this, which I'm going to consolidate all the negative. So this times this will give me 100. Then 1.01 plus this times this will give me 100 1.01 square and 100 1.01 to the power of 3. And now I am pretty confident how I can deduce the amount of saving during the nth month, because looking at the pattern that I've written down so far, I know the first term here is going to synchronize to this 5,000 and 1.01 to the power of, when it is number 1, it is power 1. When it is number 2, power 2, 3, power 3, 4, power 4, and this should be power n. Then minus away this that I'm seeing here, it is a GP with the first term as this. The common ratio is 1.01. The number of terms, 2, 1 term, 3, 2 terms, 4, 3 terms, and there should be n minus 1 number of terms, minus 1, and this divided by 1.01 minus 1. Let's try to simplify this, if everything is okay, I should be getting this. Okay, so we have a 5,000, then 1.01 to the power of n minus away this divided by this is going to be equal to 10100 of 1.01. I mean this divided by this is 10100. This, because when I look at the question, I'm supposed to express it in the form in terms of this 1.01 to the power of n, and I have a 1.01 to the power of n here. So for this, I'm going to rewrite this as 1.01 to the power of n divided by 1.01 and minus 1. So we have a 5,000, 1.01 to the power of n, this times this times this gives me 10,000. So 10,000, 1.01 to the power of n, and minus and a plus 10100. So this and this gives me a minus 5,000. So I'm going to write this first, 10100. minus away 5,000 of 101 to the power of n. And I guess this is how we are able to prove this already, just by factorizing out 100. I'll get a 101 minus away 50 of 101 to the power of n. Okay, shown, done. And we want to determine the month that Mr. Tan will deplete his savings. So for him to deplete the savings, that will mean that this amount should be less than or equal to 0, correct? So I am going to, hang on, let me erase this. I am, for part 3, I am going to let the amount of money that Mr. Tan has to be less than or equal to 0. So I'm going to let 100 and 101 minus 50, 1.01 to the power of n. I am going to let this be less than or equal to 0, and I'm going to try to solve for n. And we are looking for the for an n which is representing the month, and we are looking for it to be an integer value. So I guess we can just simply press this into the calculator also. I'm going to press this into the calculator, the left hand side into the calculator, and instead of graph, because n is an integer value, I'm going to try to generate it into a table. So second graph will help me to generate it into a table, and from this table I'm just trying to look out for those values where this entire thing, which is in y1, is less than or equal to 0. So I guess 71 is when it is starting to get less than or equal to 0. So I'm going to write into my solution what I've seen on my calculator. So x is going to be n here, and y1, which is this entire thing, so y1 is 100, 101 minus 50, 1.01 to the power of n. I'm looking for something that is less than or equal to 0. I'm going to try to write it as the middle row. So I know when it is 70, this is going to be 66.183. When it is 71, this is negative 34.16. And when it is 72, this is equal to negative 135.5. So I'm looking for something that is less than or equal to 0, and the smallest possible value for it to happen is when it is 71. So I know it is the 71th month. Can I tell you a secret? I hate this kind of question where I need to convert month to the month and year. I always find this like very unnecessary. Why can't I just end my answer off here, right? I think a lot of you probably will agree with me. So it's something that I don't really like, but I see this happening all the time. And this, if you were to just try to calculate, starting from January 2019, and if you have calculated this will end up with giving you November 2024. Okay, so since the question asks for the month and the year, so November 2024, Mr. Tan will be depleting all his money. Oh, okay. Somebody was asking why we cannot let it be equal to 0, and I guess it has been answered by Jovan, because n may not be because n can also be less than 0. We can see it from here. If we let it be equal to 0, it's not going to be that easy for us to find, because it is equal to 0 is somewhere that is in between. So the first month when he continued, because he still, by the next month, he will still have $66.183 to be drawing from, which means that he can draw one more time, and that is when all his money will be depleted. Okay, so rather than letting it be equal to 0, I would rather go for less than or equal to 0, and we can see it very clearly from here. Goodness, I was just hoping, right, that no one will be asking this question. So I hate it. I said, like, I don't hate what you're asking me, but I just hate going from here to here. So what we can try to do is okay, let me just try. Okay, so 71, every 1 year is going to be 12, so I'll minus 12, then I'll see what is the number, then I'll minus 12, I'll minus 12, I'll minus 12, I'll minus 12, 1, 2, 3, 4. Actually, I've already done it. I will be minusing 12 like 5 times, and then I'll be getting an 11. So this 11 is going to be November, and this is when 202019 happens, right? So after 1 year, it will be 2020, another one 2021, 2022, then this will be 2023, this will be 2024. So 2024, then another 11 more month, November 2024. Okay, I hate it. So next, yeah, we can also do this. Yeah, I mean, you guys can see, okay? We can take this, divide, then get the remainder, and we still need to count how many years. So it is like 12 times, I mean, like 71 is equal to 5 times 12 with a remainder of 11. Okay, I mean, I have this feeling that since suddenly of the entire question, right, this was actually the thing that triggered three different questions. So I think, can I just say that a lot of you are actually hating this kind of question where I have to convert month to year. Okay, anyway, let me quickly finish up this question, and then let me do one last question, and then we end. Okay, so now we have Mrs. Tan, and Mrs. Tan is also trying to deposit money into the bank. We are trying to, in part 4, to gauge when Mrs. Tan's money will be more than the money that is in Mr. Tan's account by the end of the month. So let's try to do a deduction also for the amount of money that is in Mrs. Tan's account. And I'm going to be looking at the month again, and I'm going to look at the total amount at the end of the month. So during the first month, January, according to what this question says, in the first month, Mrs. Tan will be depositing $3,000, and the bank is going to offer an interest of $10 for the first month. Okay, starting from the first month, and according to what this question says, Mrs. Tan is also going to be depositing $50 in the middle of the first month and starting in January. So in the beginning of January, $3,000. In the middle of January, Mr. Tan is going to deposit another $50, and by the end of the month, the bank is going to give $10. So we have this. And for the second month, the $3,000 will still remain there. Mrs. Tan will top up another $50, so 50 plus 50. I have 2 times of 50. And the bank will give now $15. So it will be 10 plus 15. This is going to be an AP. 10, 15, 20. March. This will be the amount that is already inside, and Mrs. Tan is going to be topping up another 50. So this plus another 50 3 times of 50, then plus this will be 10 plus 15 plus 20. So which means that I can deduce for the nth month. For the nth month, it is going to be 3,000, then plus 1 times of 50, 2 times of 50, 3 times of 50. So this should be 50n. Plus this is going to be an AP, the sum of an AP. So 1 terms, 2 terms, 3 terms, and there should be n number of terms, n divided by 2 times of the first term, plus n minus 1 times the common difference, which is 5. So this will be this, plus 50n plus n over 2, 20 minus 5, I'll get a 15 plus 5n. So if I were to work this out, I am going to be getting a 3,000 plus 50n plus n over 2 plus 15 over 2n. 50n plus 15 over 2n gives me a 115 over 2n. Then this times this gives me a 5 over 2n squared. So this is the amount of money that is in Mrs. Tan's account at the end of the month. And what we want to do is to look at the month when Mrs. Tan's money is more than Mr. Tan's money. And I'm going to call the difference between them, the difference between their the two amount, be, let's say, D. So D, I am going to let it be the amount of money that Mrs. Tan has, which is 3,000 plus 115 over 2n plus 5 over 2n squared. Then I'll minus away the amount of money that Mr. Tan has, which I already have gotten it here, and that is 100. And 101 minus 50 of 1.01 to the power of n. Okay, I have this. And my intention is for Mrs. Tan's money to be more than Mr. Tan's money. So I'm trying to look out for the times when this is bigger than 0. So I'm looking for D to be bigger than 0. And we are looking at, again, the month when this were to happen. So what I'm going to do is I'm going to press it into my graphing calculator again. Okay, I'm going to press it into my graphing calculator again. And the good thing is we already have y1 as this that we have pressed just now. So what I need to do is to just press this into my y2, and I'll take y2 minus y1. In case you don't know where is y2, I get this question a lot. You know, to trigger y2, you just need to press alpha trace. With alpha trace, you will get y2 and you will get your y1, then y2 minus y1. If you can just shift your cursor to the equal sign and you press enter, if you can just unbold the equal sign, this is unbolded, this will be bolded. Once you unbold the equal sign, it will not appear in the graph, it will not appear in the table. So if I were to unbold y1 and I'll unbold y2, the table that I'll be getting is just going to be for y3, and y3 represents D. Okay, y3 represents y2 minus, for my y2 minus y1. So looking at D, I am going to be looking at the table. I'm going to be looking at the month when D, which is this, is going to be bigger than 0, and that happens during the 15th month. So 14, this is minus 57.63, which means that Mrs. Tan is still having less money than Mr. Tan. But during the 15th month, 129.84, Mr. Tan's money is more than Mr. Tan's money. 16, this is 322.89. Therefore, I know this time it is the 15th month. 15th month, this is let me see, this is going to be March. Okay, this is easy, just minus 12, then I'll have 3. So this is going to be March of 2020. Okay, this is question number 9, and we are at the last question now. Let me very quickly finish the last question. The last question is actually pretty okay. Okay, let me take a look at the last question. You know, my student was telling me, one of my students was telling me that on Tuesday, because I plan to finish it by, oh no, where's my question? I plan to finish it by 9:30, and I mean, I delayed for a little bit, so I didn't manage to finish it by 9:30. So I think Tuesday we ended at, I can't really remember, those of you who did it together with me, I think we ended at, oh no, where's my question number 10? On Tuesday, I think we ended at sometime like 9:50. So my student was telling me that she went to sleep at 9:30. So I was a bit surprised. I'm not sure about you guys, but I find sleeping at 9:30 pretty tough. So okay, I mean, just in case some of you are planning to go and sleep, let me just tell you, okay, I'm going to just finish this, and I will probably take about 10 minutes to finish this, okay? 10 to maybe 15 minutes, because it is okay question. So let's try to read this question together. We are looking at the group of scientists looking at this rare species of flying fox, and the number of such species in thousands is n. Okay, so n represents the number of this flying fox in thousands. N in thousands. T is in year, and we have the death rate of the flying fox, and we have the birth rate of the flying fox, and we are supposed to be deducing this, which involves dn dt, and we know that for dn dt, just like the schematic that I draw in the tuition class with some of you, it is good, for us to take a look at the whole scenario and ask ourselves what exactly is dn dt first. dn dt represents the rate of change of the number of flying fox in thousands per year. So what I'm going to try to look out for is every year how much goes in to contribute to the increase and how much comes out that contribute to the decrease in the number of flying fox. So according to the question, the decrease, death rate, it is not about death, it is about death rate, because we are looking at per year, how much lesser will the number of flying fox be. The death rate is proportional to the number of flying fox that is present. The number of flying fox is n, so this is proportional to n. And according to the question, the birth rate is a constant of 2000, but let's be careful, it is not 2000 here, because n that we are analyzing is in thousands, so here should be 2, which means that now what we are looking at, dn dt, is going to be input positive, output negative. And since I define the input and output myself, this k which I introduced, I'm going to let it be a number that is bigger than 0. Okay, so that negative will strictly imply that this is going to be the output from the system. We are supposed to show this, and very obviously, I think we need to find k. What are the information that is given that I can possibly use to find k? I'm given 2 pieces of information here. There were only 1000 flying fox, n is equal to 1 in the at the start of the conservation. So this piece of information tells me that this piece of information here tells me that when t is equal to 0, n is equal to 1. So this is not a piece of information that I can use here, okay, because I don't have dn dt, so I'm not using this. But next, the question says that the rate of the number of flying fox per year is 1500 when the number of flying fox is 3000. So the number of flying fox is 3000, n is equal to 3. The rate dn dt is equal to 1500 divided by 1000, which is 3/2. And I think this is the perfect information for me to plant it into here in order for me to solve for n. So I'm going to make use of this when n is equal to 3. dn dt, this is equal to 3/2. So 2 minus 3k, this is equal to 3/2. This will help me to solve for k. K is equal to 1/6, which means that therefore dn dt, this is going to be 2 minus 1/6n. And if I were to multiply throughout by 6, we have a 6 dn dt. This is equal to 12 minus n. Okay, shown, done. And we are supposed to solve this differential equation like what we have talked about in, I think, question number 2 on Tuesday. There are 2 ways for us to solve differential equation. You can take a look at it on the theory outline on the Achevas TV. So I'm going to make use of that. I'm going to treat this as a variable separable. There's a very good structure that I'm going to be following. So when I have a 6 dn dt, this is equal to 12 minus n. Let's try to solve this. It is not a difficult differential equation to solve for. I'm going to divide this across to the other side, 1 over. There is a question. I'm not very sure if I will be able to answer this question, because the death rate to me is the output from the system. The flying fox die. So it is going to cause n to be reduced. And the question says that this death rate is proportional to the number of flying fox. So from the system, what that comes out of the system is proportional to what? To the number of flying fox. And the number of flying fox is n in thousands. Going in is birth rate as a constant of 2000 per year, so it is 2. That is why Kn is the output. One thing that will be very obvious is that the question will tell you what is the output. You know why? Because none of us are flying fox specialists. So this piece of information will be given to us by the question, where the question says that it is proportional, K of proportional to the number of flying fox. Sorry, I'm reading a response. Well, let's not discuss about the flying fox yet, because this question will get interesting in the last part, where they actually discuss about the flying fox. Okay, hang on. Anyway, let's continue with this, okay? So we are going to try to solve this. I'm going to bring this over to the other side, so it will be 1 over 12 minus n. And I can let the 6 stays here, or I can bring it over to the other side. It doesn't really matter, it's just a constant. So it's not going to be really affecting my integration. So I'm going to integrate both left and right hand side. I'm going to integrate both left and right hand side by t. So integrating this, 1 over 12 minus n, integrating by t, I will have this. This is equal to 1 over 6 integration of this dt. This is an easy integration, 12 minus n. This will be 1 over 6t plus an arbitrary constant. I'm going to go for a. I'm going to try to make n the subject. We are trying to make n in terms of t. So modulus of 12 minus n, this is going to be e to the power of, oops, there's a negative here. Yeah, it's negative, so I have a negative here. So this is this. So ln of modulus of 12 minus n, this is minus 1 over 6t minus a, which means that the modulus of 12 minus n, this is going to be e to the power of minus 1 over 6t minus a, which I can also rewrite it as e to the power of minus 1 over 6t e to the power of minus a. And the reason why we are rewriting this is because I know what I'm going to be expecting next. We practice our differential equations, so that there are a lot of decisions that we are trying to make algebraically, like in this case, has already been done because of our experience, not because we know through the algebra that we are seeing here that this is going to be broken up into 2 parts. So because I know later it's going to be easier, and as in like this, I'm going to make n the subject, so removing the modulus, we have a plus or minus e to the power of minus a, e to the power of minus 1 over 6t, which means that n is going to be equal to 12 plus or minus e to the power of minus a, e to the power of minus 6t. And because we have broken up this into 2 parts, now I can simplify and write this as maybe plus b, e to the power of minus 1 over 6t, where b here represent plus or minus e to the power of minus a. Okay, so n is equal to this. This is not enough. We need to check the question and ask ourselves, is it possible for us to solve for b? Let me erase this. And it is actually possible for us to solve for b, because just now we found a piece of information that we couldn't use, and that piece of information is this. At the start, when it means when t is equal to 0, n is equal to 1,000. N is in thousands, so n is 1. So I'm going to make use of this. When t is equal to 0, n is equal to 1. So we have a 12 plus be to the power of 0, which is going to be 1, is equal to 1. This tells me that b is equal to minus 11. So n that I'm looking at here is going to be 12 minus 11 e to the power of minus 1 over 6t. Part 3. Part 3 is very easy. I'm not sure why Real Valley actually gave 2 marks. It's very, very generous. Hang on, I'm reading a question. Let's see. A question that is posted by you. Wow, I have a bit of problem looking at this question. Why don't I say plus minus e a equal to B and skip a step in simplification. Okay, I think I'm going to skip this question. I'm so sorry because number one, I'm not very sure I've understood your question correctly, but that was what I did, I thought. So I'm going to skip this, okay? And just in case you are talking about okay, I think I shouldn't assume the question. So part three, we are talking about for the number of flying fox n to be more than 6,000. Oh, no, more than 6. Because n is in thousands, so we are trying to look at this to be exceeding 6,000. So this should be more than 6. We are looking at 12 minus 11 e to the power of minus 1/6t to be more than 6. I guess I'm going to just press this into the calculator. Let me show you what I have when I press this into the calculator. I will be pressing this into the calculator and I will generate a table, and this is the table that I've gotten. So I'm looking for something that is more than 6 for when x is equal to 4, that is when y1 is more than 6. So my answer here is going to be looking at t, looking at n. When t is equal to 3, this is 5.3282, not bigger than 6 yet. When it is 4, this is 6.3524. And when it is 5, this is equal to 7.2194. So when it is 4, according to what I see on my graphing calculator, is when it happened. So deduce the minimum number of years. Minimum of years is 4. So this one, done. Sketch, I guess this is also pretty simple. We are supposed to sketch n. Oh no, I've erased n. So n is equal to, let me rewrite it. N is equal to 12 minus 11 e to the power of minus 1/6t. Sketching this easy graph, it is going to be a graph that looks like this. And looking at this graph, I would suspect that there's going to be a horizontal asymptote. Doing a quick test, when t tends to infinity, n tends to 12 because this will go to 0. So that justifies for me a horizontal asymptote. My graph is going to be like this. T, n, it starts from here. I'm going to go for a solid dot here. Then you will have a asymptote, like what we were saying that day on Tuesday. Actually, it was just Tuesday. We should always try to sketch in the asymptotes first before I sketch in the rest. So we have this. And it is going to be tending to 12. When t tends to infinity, this becomes 0. So it tends to 12. And when t is equal to 0, this is going to be equal to 1, which was what the question has mentioned. When t is equal to 0, n is equal to 1. So I have my graph as this, and suggest what is the long-term behavior. I guess in long run, the number of flying fox will just be 12,000. Okay, so I guess that's it. The number of flying fox will just 10 to 12,000. And part 4 suggests a possible limitation of this model. In part 1 suggests a limitation of this model. Actually, let me just read for you River Valley's solution. I think it's a very interesting solution. Interesting question with a equally interesting reply from River Valley. River Valley says, because this is just 1 mark, so you can give any possible limitation where the model failed. For example, an outburst of natural disaster, or an increase in the hunting of flying fox, or maybe adverse effect due to climate changes. It may sound like, oh wow, this is common sense, but let me read to you one more time, okay? And can you see the similarity between the 3 possible suggestions by River Valley? So number 1, it can be not necessarily this. Okay, so they are suggesting you can say things like there's an outburst of sudden natural disaster. Number 2, an increase in the hunting of flying fox. Number 3, adverse climate change. So why do they quote this? All this thing is targeted on one thing, because in order for us to build this, just now we have started off with looking at dn dt. And we are talking about what that goes in, and we are talking about what that comes out. What that goes in is 2,000 per year. What that comes out is going to be kn. This is going to be the birth rate. This is going to be the death rate. So we build our model by looking at the birth rate and the death rate. Can we change, the number of flying fox that is going to be birthed? I'm not sure, because this is a rare species of flying fox. So the chances of us reintroducing new flying foxes into this part of Australia, I don't think it is very, yes, it is possible, but I would rather work on the number of flying fox that die, because this is about probably natural death, which means that if I were to try to target on the limitation of this model, the limitation is most likely going to be from the death. Because if birth is not within the control of the environment, okay, not control environment, what I'm talking about, if birth is they're just going to give birth. Okay, so if the flying fox will just continue to give birth at 2,000 per year, that means death, if it is not natural death, that is what River Valley was replying to this. They are quoting all the unnatural death, natural disaster, hunting, climate changes. I think it is a good answer. So last part, 1 mark. Wait. Use your creativity, but at the same time, you'll be better if you talk about the death instead of the birth rate of the flying fox. Okay, this is the last question, and and okay, that's it for tonight. Next week, actually, I'm